So in previous weeks, we have played with CAN, and we're going to continue that again today. There's a bit of tidy up that needs to happen. The applet's currently in a bit of a state, to be honest. And there are some things that need to be fixed up still. So the end of the frame is still a bit woolly and unknown. The CRC is done, and the framing. So we need to get the packet out into the PC. So that's currently in sort of a byte stream, which is not necessarily the best way to be handling that. So I think first up, I will probably get on with some cleanup. It's going to be the most enjoyable thing. I apologise for that. So if we dig into the code, I'm just going to take a commit of where we are. I haven't done anything since last week, I'm afraid. Apologies for that. So then, if anyone has any questions or wants clarification or anything like that, please do feel free to shout, and I will do what I can to address your questions. Otherwise, I'm just going to sort of work my way through it and talk about it as I go. So at the top here, we've got the CAN bus module, and this will take care of wiring up the signals to the pins. It connects up the transmit and the receive pin as well as the termination pin. We want to be able to set that termination pin from the command line. So it'll either be in the reset state or it'll be somewhere in the elaborate, probably the elaborate, so that we are able to then, by tweaking the command line options, we can then change where the termination is turned on or off. Hi Mount Joy Guitar, good to see you. So I think that's something that's going to come up later on, and I'm going to keep track of these in the to-do file. So we want to termination on the command line arguments. I think that's a comment that can go away. Oh, David, sorry, I did see your message on Twitter. I didn't get around to replying yet. Apologies for that. I'm not sure yet about distributing in US or anything like that. I think it would be nice to do. I'm not sure if Peter Esden might be willing to sort of have a look at taking these boards on or something. They're not super complex, so if you are up for placing some parts, then that might be a route forwards for you. But certainly this is something that I think a few people are pretty interested in, so I'm going to try and do what I can. The stuff I've done previously, so I did a small run of Glasgow boards, that was kind of restricted to the EU, and that may now be even more restricted thanks to Brexit. So if I am to distribute these, I'm going to need to sort of look into what's required from that point of view. Yeah, I mean, if you're willing to give it a go, then it's not a bad board, I don't think, to start out on. There's nothing too complex on there. There are some hardware revisions, so I probably wouldn't go for it just yet. I need to make some tweaks. And actually, let's have a quick chat about that. So this camera here, there we go. So down here we've got the termination, transmit and receive LEDs. I don't know if you can see that actually. It's blinking away. So you can see this one here blinking. And this one is just so dim. This is in part because it's not being driven very strongly. And I think it's also in part because it's on for such a short duration that you get the sort of a dimming effect on that side of things as well. So I think some tweaking to the resistor values there. There was an issue with the pinout for the CAN transceiver itself. And we haven't actually verified that the termination works properly yet as well. So that's something else to do today. Let us put that on the list. Verify termination works. We can do that once we've got it on the command line documents. Good stuff. Okay. You have to wait a few months for your Glasgow anyway. Fair enough, fair enough. Okay, so I think largely the CAN bus module is good to go, aside from that termination. This pin is shorted to indicate, so sorry, I'm reading my comments now. This pin has a shorted indication LED. So that is a comment from before, and I've actually fixed that up now, so that's good. And we can get rid of the works as well. So we've got the transmit, termination, and the receive. Cool. Then we move on to the low level, and this takes care of the timing for the bits, as well as the stuffing, the bit stuffs. So in this module, I think this is going to need a good cleanup. We've got the ability to give it the receive signals. There's no transmit timing yet, so that's something we need to look into, I think. The bit boundary, I think we were going to try and use for the ACK, which could well be used for transmit as well, but we need to sort of have a think about that one. Aside from that, we've got the trigger, which is the start of the first bit. We've got a run flag, which says whether you should continue running. We've got then an RX ready, which is a strobe which happens when the bit, or at the sample point of each bit, and the RX ready raw, which then also happens on every stuffed bit as well. So the RX ready has no stuffs, and the RX raw has the stuffed bits. And then we've got the RX data, and that's a shift register which takes one bit at a time into it. And I think that probably needs to be adjusted because it's 32 bits long, which is probably much longer than we need. And I'm not sure if the register really should be here or somewhere else, so let's have a think about that one. The debug signal, I think we can probably get rid of. I will perhaps keep it just for now so that we can refer back to it while we're doing the cleanup and kill it off later. That's something else we need to do is variable bit timings or baud rate. So at the moment we've got the bit cycle is 19, and that is 19 ticks of a 48 megahertz clock. So 48 megahertz is, I can't remember off the top of my head. Let's grab a calculator. 48 E6, so 1 over that is about 20 nanoseconds. 20.8 nanoseconds. And then we've got 19 of them, so times 19 is 30 or 395, is that? 6, 7, 8. 6. Oh gosh. Okay, I'm just going to copy it here. I hate doing these things. 6, 8 is that. Yeah, 395. And then 9 is that. So 395 millimicro nanoseconds. So that times 19 equals approximately 395 nanoseconds. And if we then reverse that, so 1 over 395.8 nanoseconds is 252. Oh, sorry, oh, that's a bit wrong, isn't it? What's going on there? 48 E megahertz is 20 nanoseconds, 20.8 nanoseconds. 20.8 nanoseconds times 19 is then 395.8 nanoseconds. Millimicro nano, yeah. And then 1 over that. That's unexpected. Okay. The issue is here that we actually have time quanta. It does have engineering mode, I think. It's not a bad idea. Oh no, sorry, it's got scientific mode. Never mind. That's a good call though, hard crash. So what we're actually doing, I remember now, is looking at grab the diagrams we've been referring to previously. So the bit time here is split up into the synchronize, propagation, phase 1, phase 2, and the sample point is between phase 1 and phase 2. And so what we've actually done is split this nominal bit time up into 10, which means that this rate here is actually 10 times faster than it needs to be, which is why we get the 2.5 megahertz. So 1 over 395.8 nanoseconds is 2.5-ish megahertz. Now that is then formed here. So we've got one sync, 3 units of propagation, 3 units of segment 1, and 3 units of segment 2. So if we want to produce the bit cycle counter in the alternate, the other way up, so we give it 250k baud, 250k baud. We first of all need to take the quanta times 10, and then we need to take the 48 megahertz clock and work it through. So period of cycles is going to be 48e6 divided by the quanta. Can't do spelling tonight. Is that going to be right? So 250000 times 10, and then 48e6 divided by that is 19.2. That's good. And that then obviously needs to be an integer. So we can do / to round it for us. It's not going to be precise, but over the duration of a single frame, it should be good enough. Does Python give us, so if we do 9 divided by 10, do / it gives us 0, so it floors it. And we probably actually want to round that. 9 by 10 / 0, comma 0. There we go. And what we actually want to do is get an integer out of that as well. So if we go 5, so 5, yeah, so 5.1, I guess, would go up. There you go. Okay. So let's use round then instead of divide here. Zero, and then we want an integer around that. Just look up, can Python round integer? Let's do Python built-in. Hate the way it always gives you other stuff. Oh, is it not a... Yeah, it is. There it is. Okay, so we can omit the number of digits and it will just round it to the nearest integer. So I wonder if... so ceil and floor will do, math.floor will do what 9 / 10 would do. So 9 / 10 is the same as math.floor 9 divided by 10. And we don't want to do that. We want to go to the closest. So we want to actually round it. So if like 0.4 goes down and 0.6 goes up, for example. Otherwise, we're going to have a greater error we could have avoided. So 9 divided by 10. Yeah, that doesn't give an integer. That's good. And as soon as you give a comma 0, that gives you a float. Interesting. I didn't know that. Okay. So that's cool. Now we just need to be able to configure the baud rate via the command line. So we can get rid of these. So the times 10 is to permit the time quanta in bit. No, that's all right, no worries. Thank you for your comment. Okay, 19 for 250k bits. You can get rid of all this then. That's cool. Now the sample point is actually something that can be varied in a number of IP blocks, and I think for this, I think I'm just going to leave it hard-coded for now, but this could become part of like a wish list item. Do now versus wish list, and in here we're going to make it so that the sample point is configurable. So this is the bit, what do we call it? Bit boundary. Then we got this 1 sync time, 3 propagation, 3 seg1 sample point, and then 3 seg2, and then it moves on to the bit boundary again and repeats. In terms of the number of time quanta per bit, I think that 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is what's used in that example there. If we have a look at the CAN document as well, I wonder if this tells us how many we need to have. I suspect it's not going to. Bit timing requirements, page 27. It's going to be not the right page, isn't it? Page 25, 6, 7, there we go. So, normal bit time can be thought of as being divided into separate non-overlapping time segments. These segments are synchronization, propagation, phase, segment 1, segment 2. It doesn't actually tell us how many, time quanta here. The time quantum is a fixed unit of time derived from the oscillator period. There exists a programmable prescaler with integral values, ranging from at least 1 to 32. Starting with a minimum time quantum, and the time quantum can have a length of m times minimum. Length of time segments. Sync seg is 1 quanta long. Propagation is programmable to be 1 to 8. Segment 1 is then again configurable 1 to 8. And segment 2 is the maximum of phase 1, segment 1, and the information processing time. And then the information processing time is less than or equal to 2 time quanta. The total number of time quanta in a bit time has to be programmable at least from 8 to 25. Okay, that's quite interesting. I think let's leave it as hard-coded to 10 at the moment, with the other segments being hard-coded to 1 and 333. And we can come back to that and revisit it. What was it? 8 to 25. Total number of time quanta in a bit time has to be programmable at least from 8 to 25. Okay. So we can come back to that some other time. Now then, we've got a counter, 32 bits, probably doesn't need to be that big, and that's used to count the number of bits we've seen. We can then get rid of these two commented out variables, and we've got the Rx last and Rx stable count, and this is what we're using to implement the destuffing. The debug there is set to when the stable count is equal to 4, so that's giving us visibility on when the stuffing is taking effect. I think we are able to just get rid of that, so let's do that now. Let's get rid of the debug here as well, and we probably need to get rid of it somewhere else as well. Low level debug, so let's just get rid of that line. I'm gonna skip this music if that's alright with everybody. Okay. So the initial state is idle, and this is where we stay until we get the trigger, the start of frame. Again, if we refer back to the Wikipedia page, let's use this one. The start of frame is when the line goes from recessive to dominant, and let's have a look at the code. if self.rx trigger, and rx trigger is what? That is the inverted of the bus receive line. So I think that's effectively can high. Although we don't actually get that signal out of the file, the line driver. So the last bit is set to 1, and that helps us to reset the bit stuffing algorithm. Now, because the last bit here is then shifted in, assigned to the current input data, once we see the start of frame, it's going to be different to what it thought it was previously, and it's going to then reset everything. So we can just put a little comment in there, reset the D stuff. I'm kind of tempted to separate the D stuff out into a separate module, but let's see how that goes. Now the data, that's that 32-bit register, I think, which I am not convinced we want to use or don't want to make available here. It does take care of the bit stuffing, but we've already got the signal or the strobe that's being output to the other module, so we can take care of the data in the other module. Let's just see if we're actually using it in the other module at all. Yes, we are. Okay. So for that reason, it might be actually kind of reasonable to keep it. And that way we can use the strobe to indicate that there's a new bit. And we can then immediately access the data for the last n bits that we have. Okay. Let's keep that then for the moment. I might remove it. Let's put a little comment on it. Where is it? There you go. Hey Rod, how are you doing? Right. Now the counter is on the trigger is set to 0. We can move that out into here. That doesn't need to be only happening then. And again, the RX stable count can move out. And that actually is now paired up with the RX last. So I'm going to call these something different. I'm going to call them D stuff or something. D stuff last and D stuff RX stable RX count. Oops. Ah, good stuff. Glad to hear you well. Yeah, no worries. I don't know about osmosis. I like to have things on the background as well, but I always find I get drawn in. Now the D stuff algorithm will count the number of bits that are the same and skip the greater than or equal to 5. I think that's the 6th bit, isn't it? Go back to Wikipedia. I've got some reasonable diagrams here. Oops, have it on a new tab. So 1, 2, 3, 4, 5, skip. So yeah, I'll skip the 6th. Oh, neat. Got the cutting edge of USB over there. Skip the 6th bit. Cool. Now to count to 6, we do not need 5 bits. We only need, what do you think? 1, 2, 4, 8. So yeah, 4, 2, 3, we only need 3 bits. and that can actually count all the way to 7. So that's good. What we can do then is range 6, and that should allow us to have a signal which is big enough to hold 0 through 6, I believe. Or is that going to be 0 through 5? So here we go. Range 51 creates a constant of 10 whose size is large enough to hold any value between 0 and 50 inclusive. Okay. So if we actually want to include a 6 in that point, yeah. So if we actually want to include 6, we need to do range 7. And that would be 0 to 6. Okay. Then we need to rename them, don't we? Okay. So that takes care of resetting the dstuff algorithm. This will then take care of resetting the shift register. And then the counter is used to deal with the bit phase, or the time counter. So what we can do is just pre-calculate some values up here. So we've got
isn't necessarily a thing you achieve.
Time value of before sample is going to be sync plus prop plus seg1, and then t bit time is going to be sync plus prop plus seg1 plus seg2. And actually we then have the cycle counts as well. I'm going to reword this to be before sample t, bit time t, and then we can do before sample t cyc times the bit cycle, or bit cycle count. Does that work? Counter, yeah, that works. Cool. Because the counter is going to increment on every tick of the 40 megahertz clock. Time. Yeah. Not totally comfortable with these variable names. I'll come back and get them in a later point, I think. So on the trigger, we then assert the bit boundary, just temporarily, combinationally logic, which gives us a pulse on it. And I think that's good. If the counter is then equal or greater than the before sample t, that's a really bad name, isn't it? What are we going to call it? Where's the diagrams here? Bit setup, maybe bit time. Bit setup cycles, isn't it? And then down here, on bit phase 2, bit phase 3, there we go. Got to sort out those state names as well because they're not quite right. And a bit time cycle, was it? Bit period cycle. Call that period, not time. So. the next line. Where are you pointing, David? Before sample T. Oh yeah, thank you. Bit sample, bit setup. Bit setup T. There we go. Okay, that's much better. So this is the time from bit boundary to sample point, and then this is the time from bit boundary to next bit boundary. Cool. Okay, so the bit phase 1, that is what is actually referred to in the spec as the, where's it gone? Sync, prop, and phase 1, or segment 1. So let's call that setup. And we then count up until we reach the target. And once we reach the target, we do some stuff. So first of all, we will keep track of the D stuff. This is where I think the D stuff really needs to go in another module, because this module should just be about bit timing, I think. Excuse me. A bit too much going on here, isn't there? Okay, let's tease that out in a minute, I think. So it keeps track of what we're seeing now and what we saw before. And if it's not the same, then it resets that counter. Else, if it's greater than or equal to 5, so we've seen, where is it here? We've seen 5 bits already, we skip it. And this is actually an error which we're not handling properly. This is a framing error, which means I think we need to abort the frame and just do nothing until it stops. I'm going to leave that on the to-do list and we can come back to do that. Handle bit stuff for RAWs. Otherwise, we increment the counter. And by incrementing the counter, we then get to the point where framing error is a good point on the spec. I suspect it would be, I think you're supposed to stamp on it. Error detection, error signaling, there you go, 23. 22, 23. So, stuff error. A stuff error has to be detected at the bit time of the 6th consecutive equal bit in a message. It doesn't say what to do about it, but error signaling. A station detecting an error condition signals this by transmitting an error flag for an active error. Sorry, an error active node. We need to then go and look up what an error flag is. Okay, so error flag. Oops. There you go. An error frame consists of 2 different fields. The first field is given by the superposition of error flags contributed from different stations. The following second field is the error delimiter. Active and passive error flag. Blah, 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 blah. 6 consecutive dominant bits. Passive error flag consists of 6 consecutive recessive bits, unless it's overwritten by a dominant. Yeah. Now, that's interesting because I don't think it's in here. There's the end of frame, and then there's the end of frame separator or gap. Here it says the data frame goes there, and then we get an error flag. I think I might need to go away and read that a bit more, inwardly digest it. End of frame or error delimiter or overload delimiter, and you get an overload frame, which again conveys error state. Yeah, I'm going to go away and read about that, I think. Interframe spacing is what we're looking at just now on the diagram. Data frame and remote frames are separated from preceding frames, whatever type they are, data, remote, error, or overload frame, by a bit field called the interframe space. In contrast, overload frames and error frames are not preceded by an interframe space, and multiple overload frames are not separated by an interframe space. In contrast, overload frames and error frames are not preceded by an interframe space. So that sounds like we would stamp on here if we're putting an error frame on the bus, I think. But let's leave that out for now. we can come and have a look at that. Read up on, what was it called? An error frame. Yeah. Hey Omni, good to see you. Thanks for joining us. We're doing a bit of tidy up. Okay, so step one is there if we have seen a bit that's not the same, we reset the counter. If we have seen more than 5, then we have to flag it, and that's something we can do later. Need to think about extended IDs too. Yes, indeed. I think that's something to come. Let's put it on our list. I'm going to put it on the wish list for now, but I definitely want to handle them. Otherwise we just count it as another same bit. Here, this I think is if the stuff counter is less than 4. So what we can do is go 0, 1, 2, 3, 4. I feel like this is another off by 1 type error. If that counter is less than 4, take in a bit and go to bit phase 2, which we need to tidy up as well. So 0, 1, 2, 3, and it will be the same there, but here it will actually be, 0, 1, 2, 3, 4, 5. Is that right? Less than 4? No. 0, 1, because it's out of cycle, so actually, let's draw on this. What we actually have is effectively nothing, and then we got 0, 1, 2 out of phase, 3, doing really bad mouse drawing. This then becomes 4, and you can't see it because it's pink, red on pink. And then at that point, so I think that yes, that is actually okay. So let's keep that as it is. It would be nice to do that more properly, I think. Again, when we tease these out into the sample points and the destuffing and the data receive, I think there's going to be 3 modules out of this. Now, bit phase 2, bit phase 3, I think we can just move that into here. This can become a generic, and we can get rid of that. I think that will still work. And that else has died now. Yeah, that else has gone away, which is good. Okay, have we made enough changes to give it a test? Now, what I was doing earlier is I was just sending the date in, or the timestamp, the Unix timestamp, so that we get new data every period. You can see that on the scope that's changing, and because of this stuffing, the length of the frame actually wiggles around as well. It's not a constant time based on the size of the data. It depends on the contents of the data too. So let's run this and see what happens. Bit phase 1 reference but not defined. Okay, because we called it something else now. Bit phase 1 here, so that's now actually set up. I don't want to use hold because I feel like that's the wrong thing to be calling it, but I'm going to call it bits weight maybe. Oh, oh, broken. Typical. Oh, it's got valid CRC, yes. That's unexpected. Oh no, okay, it's not always saying yes. Okay, if you look at the scope, you can see there's a bit of stuff going on in there. And that looks like it's possibly around the CRC in the frame, perhaps. But that red line, I think, will indicate... What does that indicate? I think that is... so that's 89, so that's the debug arb pin. Find out where that is. Pads. Debug arb. There it is. Oops. And I think that will debug arb. Can't do typing. That will, yeah, that indicates that the frame is ongoing, that we're not in the idle state. So for some reason, it's falling out of the frame before the end of the frame. What have we changed then? That's all okay. I'm gonna do a git add -p, which allows us to stage chunks. That's just comments, that's good. That's just a comment. We've removed the debug signal, don't care. We've reworked that. Now I'm pretty sure this comes true, so let's just do Python and quanta equals baud rate times 10 bit psych round 4886 divided by quanta, and then bit psych is 19, so that's good. Yep, keep that. That's just comments, that's just comments. Ooh. Oh, okay, that's all right. Let's actually rework that so that the patch looks a bit nicer. Just gonna want that here. Oh, and everything else is gonna go out of sync, okay. I have to look at that in a larger sense. Okay, so the module is still being created. We've added these timing doodads, and they are being swapped in. So where we've got the bit period cycle, bit period cycle, we swapped that in. So we had previously sync plus prop plus seg1 plus seg2 times bit cycle, so that looks good. That's okay, I'm happy with them. And then we got the setup cycle here, which was previously sync plus prop plus seg1 times the bit cycle again, so that's okay. Got rid of the LSB counts, but that's fine because they're comments. Now we've got the counter, which is still in place. Actually, just going to move these, I think. No, I'm not, because I'm going to break the patch. That's good, that's good, that's good. The debug thingy has gone away, and we've then renamed the RX last RX stable count to dstuff RX last. Now this could be a size issue, potentially. What do we want to see? RX last versus dstuff RX last. RX last versus dstuff RX last. That's better, right? Okay. So in the old code we had RX last set to 1, which we're still doing. Let's just change name. And then down here we set it to bus RX, which it's still doing. Yeah, so that's good. Okay, and now we got RX stable count versus dstuff RX count. versus D stuff RX count. Now previously, oh, we were using it in the debug signal. That's okay, we can ignore that. It was 5 bits, and I'm now doing range 7. I wonder if that's part of the problem. We can try that in a minute, maybe. We were setting it to 0 after the trigger, but now we're doing it all the time while we're idle, which should be fine. We was previously setting it to 0 on a mismatch, pairing it against 5 and resetting it to 0, and doing +1 and comparing it against 4. So that hasn't changed, which I'm surprised by, because I feel like this is a bit stuffing error. So let us change that. This range 7, I think we need to make that into just a 5 again, 5 bits wide. Run it again, see what happens. No, that doesn't look happy, does it? Still wrong. That's not the problem. I will put that back. Oops, put that back to 7 just for now. Have a look at what else we could be changing. LSB count stuff. Okay, let's actually just clean this up so we can commit stuff that we genuinely want to get rid of, like we want to keep that. We want to get rid of one of them. Keep that. Don't do that. Yes, yes. No. No. Want to keep all of these. Keep all that. Oops. What crimes are you committing? I'm trying to just tidy things up so we have a clean understanding of what is actually changing. Yes, get rid of that. So then we have, oops, got these changes still to review, and in here is a problem. I wonder if it might be related to this potentially. Removing that extra state. Oh yes, I think it might be actually, because what we currently have is the data being updated in clock 1 and then clock n, and then clock n plus 1 you then get a strobe saying that it's ready to look at. So I think that is actually probably an issue. Let's turn that back. Where are we going? Up here, bit weight. Bit sample, and we can do bit weight. Grab that. Okay, I think that might help us. This is another situation where it might be good to tease that out. There we go. Yeah, that's better. Okay. You can see now, if you look at the data, I'll put the scope back on. You can see the data here is 9, 10, 11, 12, 13. So that's the time in seconds since 1st January 1970, Unix timestamp. I'm just using that as a dummy data for now. So that's icky. I don't like this. I want to not have that anymore. But there we are. D stuff algorithm. I guess get rid of that space because that's nasty. Yeah. Okay, this still works. It's a bit cleaner than it was. Now the D stuff needs to move, needs to shift out of here. This should be just responsible for the bit time, or the bit sample point, I think. The D stuff is then based on the sample point. And once we have a handle on the D stuff, we can then have a handle on the data actually coming into a shift register. So let's look at that. I'm going to put that on my to-do list so I can tick it off. So we've got the timing, we've got the D stuff, and then we've got the shift register. Do we actually need to hang on to the bus? I don't think we do. Oh yeah, okay, because we got that. Although for the timing, we don't need to hang on to the bus, so that's good. We just need to reference it in the init. Rx run, we still keep. Do we need to invert that? Rx trigger. No, we can invert it over there or something, can't we? Let's just keep it here. So yeah, we need the Rx run signal here because this tells the timing system to keep going. When we've then finished the frame, we can deassert Rx run and it will go back to idle. I'm going to rename that away from Rx run to just run, I think. Rx trigger is fine, and bit sample is going to be the name of that strobe. Probably a STB or something. Bit STB, let's call it STB. STB strobe. And we don't need anything else, I don't think. The clock frequency actually is available from the platform. So we should probably do that instead of hard coding it to 48 megahertz. Put that in the to-do list. Okay, we need these timings. This is where we need two panes open. Okay, so we keep these, and actually these could be in init really, couldn't they? They do not need to be here. I will leave them there for now. Then I got the module and the counter. The counter is that's what we need. So that counter there deals with the time quanta, and that then produces the bit timing as well. We can get rid of that. Look at that. Ooh. No. Yes. Oh, sorry. Yeah, good point. Get rid of the scope. So I'm just using the right-hand one as reference, but it's good for you to be able to see it too. Now, we need to reset the counter to 0. We don't need any of the other stuff in there. And self dot still called Rx trigger, yes. boundary, bit boundary. Okay, so we've got a sample strobe and a boundary strobe. Let's call them that. That makes a lot more sense. Boundary strobe and sample strobe. Sample point. And this is the for RX bit boundary. Okay, that's better. What do we call it? We called it the boundary strobe equals 1. And then move on to the setup phase. Set up phase. Okay, and in here we count until we hit this. And then we poke at the self.sample strobe. Bit weight, I think. And in here we then keep counting. And actually we don't need to do that at all, because now that we've simplified everything, we can say if it's what can we do? Okay, so if it's equal to the setup cycles, we can toggle that, strobe that, and then if counter is greater than equal to the bit period cycles, then we can do strobe the boundary bit, and we can then also determine if we want to carry on. So if if we are still running, then we go back and start again. Otherwise, we go back to idle. That's much easier to follow, isn't it? Let's call that setup. Let's call that run. Okay, there we go. So this state machine will sit in idle forever and ever until we get the trigger. And at the moment, we've only got an RX trigger. At some point, we're going to need a transmit trigger as well. When you get that trigger, we then give a boundary strobe and move on into the run state. In the run state, we're going to go round and round and round. And we will, let's move that out of there, I think. And do if it's no longer running, go back to idle. Okay, so in the run state, we'll go round and round and round. When we hit the setup cycle count, then we will strobe the sample line. Then when we hit the bit period cycle, we will hit the boundary strobe and reset the counter to 0. And then if we're not being asked to continue running, we will go back to idle. Now we can actually simplify this further by putting 2 of these things in combinational logic. So sample strobe equals counter equals bit setup psych. And then the boundary strobe counter equals the bit period psych. Does that work more nicely, nicer? I think it's probably a little bit less easy to read as well as the fact that we're doing these things in the second one. So let's not do that. Okay. Okay, that should be now something that we can use. CAN timing, we can use that in the low-level module. We need to return M in here. Return M, there we go. Self.timing, CAN timing, and we give it the bus, I think. Is that all we gave it? No semicolon, been in C world recently. Yeah, so CAN timing, give it the bit. The bus, spelled that wrong, bus. And then from that, we get the bit boundary. We get the RX trigger, no longer care. RX run, we do care about. RX ready and RX ready raw. So those have changed name. And they're now also in that timing module. So in here, I think we actually want to now no longer trigger on the RX trigger, but we want to go on the timing.bit boundary strobe. We don't need to give that anymore because that's not your job anymore. I'm going to split this so that we can deal with cleaning up two ends of the file at once. There's another one here somewhere. There it is. Don't need that anymore. That's not your job anymore. Okay. So we move out of idle on that boundary strobe. Do I need to reset the strobes anywhere? I don't believe so. Because of the combinational logic, so that means it's not registered. It doesn't have a register. It's not sort of maintaining its state. It will, if you assert it to, or if you set it to a 1 here, then it will return to its reset state when you're no longer sort of wiring it up that way. So that should flop back to 0 once we're no longer in this branch here. Does that make sense? Okay, so D stuff is going to get pulled out, but not yet. Counter is not your responsibility anymore. That's what I was looking for. Counter. Okay, and all of this stuff. So the baud rate, the setup time, and the counter. Oops. So it lasts for 1 system clock. That's correct, yeah. Because this is all synchronous, the state machine advances on a synchronous clock. You effectively you are in the run state, and then your value of counter is greater than or equal to bit period cycle. So yes, this line here takes its state for 1 cycle, because we're then resetting that to 0. Same again here. It's equal to that for 1 cycle because we are incrementing it here. That might get dual driver because we're setting the counter in 2 different places, but I think this one will override the other one. So we'll come to that in a bit. I think that's what we're already doing as well, so it should work. Okay, the counter is not your job. That's not your job. And actually, what we want to do is with m.if self timing dot sample strobe. That's not your job anymore. Still doing D stuff in here, which is a little bit frustrating, but we'll pull that out in a minute. The RX ready raw. So that's because the D stuff is still happening here. Is okay, kind of. Now the next thing is that this has 3 states. So you've got the setup, the sample, and the wait state. And that's kind of no longer relevant because we've moved the time quanta handling into another part. I don't think it's going to be super simple to get rid of right now, so I'm just going to reword that to self timing dot boundary strobe. And then we can hopefully condense these into 1. Yeah, correct, Omni. Yeah. Oops. Although I will need to put it in both the and else and also in this one as well. Well, I can move that into a wire on its own. So shall we see if this works? I have a feeling it's not going to work. It doesn't work. What a surprise. Low level RX trigger doesn't exist anymore. So 254. That is no longer called low level RX trigger. It's called low level timing dot RX trigger, I think it was it? Yes. Count is not defined in line 175. That's fine, we can get rid of that. Count is not defined in 179, again, we can get rid of that. Runs not, oh, yeah, bleh, something going wrong there. Created but never used. Oh, I never did the submodules thing. Okay, so we need to do here m.submodules plus equals self.timing. And timing has no attribute boundary. I spelled that wrong. With a n. Boundary. There's no RX run. Line 101. It's not called RX run anymore, it's just called run. How's that? Oh, wrong. Oh, no, it is wrong. Okay. So if we pop the scope on again, you can see there's a little bit of red in all the wrong places. A couple of wrong places, actually. So what's going on there? Okay. Now, this one should be giving the sample strobe and the boundary strobe. I think they should be correct. I don't see a problem with that. I'm going to... It's not complaining about the dual driver thing on that counter, so that's good. This data is very wrong. Why don't we have a look at the scope for a second? I'm going to go and zoom in. Ooh. Well, that's interesting. Oh. Yeah, okay. That red line is supposed to go high when it's not in a frame. Let's have a look, see what that might be about. High when it's not in frame. The red line is attached to pin 9. Oh, it was high there for a very yeah, or very brief period. So pin 9 is the debug arb again. Debug arb is here. There we go. Okay, so that's actually in this idle at this level. Let us, what are we going to do? Have we got pads available here? We've got the bus available. Let's put it into self.idle is going to be a signal, which we can then put here. Oops. I missed a bracket off that. Okay, so that's now a signal we can use from the low-level timing. So if we do low-level timing dot idle. Oh, oops. Okay, what do we see? What do we see? Oh, that looks quite good. No, it doesn't. Okay. So that red should go down, it should remain down for the entire duration, and then it should go up at the end. I have a feeling the issue we have is that we are never setting the run signal, so we're never asking it to carry on. think that's exactly the problem. Yeah, it's unsure about life at the moment. Okay, So previously we had a run signal here at RX ready run, and that's no longer relevant in this block. But I bet you it's being set somewhere. Oh, have I removed it already? Oh, there it is. No, that's not it. Sorry, I'm going crazy. Ah, this is set from a higher level. There, it's set there. Okay, that's really... No, that is correct. Okay. What we need to do then is m.combinational self-timing.run equals... don't really want to do that, but we're going to. Oh, I know what we can do. Get rid of that. RX run. Yeah, this is getting a bit yucky. What do we think? There we go. That's good. Okay, so that was the problem. Now this works. We've got the timing takes care of that. I'm going to tidy these up a bit because they're a bit long. Multiple lines and unnecessary. Oops. A bit of alignment because that's always nice. Okay. Oops. Let's run that again just to make sure it's still going. That looks alright, doesn't it? Cool. I'm now going to have a rummage for anywhere that uses the platform to grab the clock speed. Default clock frequency, I think that's it. Yeah, that'll be the one. Platform.default clock freak. And that'll be in hertz, I'm fairly sure, so we can just plop that right in here. Oops. Clipboard versus, Vim's copy paste. That should still work. It does still work, yay, okay. So in our to-do, we have done this one. I'm going to put an X on it. What am I going to do? Put an X on the front. And we've done this one, that's cool. Continue running. How do I feel about this stuff? Get rid of the idle one. Let's put no, not put that. So I think the timing module works well. I'm going to commit that now. And, oh no, I've broken it. No attribute idle. Oh, I was trying to use the debug, wasn't it? Get rid of that. that should now say what we want it to, still on the red line. Running, there we go. Yeah, cool. Okay, so the timing works. I'm going to commit that. Fine. Ooh, lots of stuff. Okay. Next up, we need to do bit stuffing, and that's going to happen at this level. We've got the CAN timing, which is good, and then we need the class CAN D stuff. And the D stuff is now going to happen on the bit, on the sample strobe, and it will need the bus and it will need the timing. Okay, get rid of the scope. So it needs the bus and the timing, and from that we can then, oh, we do actually need to know the idle state, because the idle state will reset this to, start the stuff algorithm again. So this is actually something we need to keep. Now the idle here, the nice thing about that is that it will only return idle once the final bit has completed. So that is actually something we should keep. That's good. Okay. Now, I don't think we need any state machine in here. Excuse me. Ooh. If we are idle, we have the stable count, we're going to call it, equals 0. There's a D in there. Otherwise, LF, we are on a self.timing.sample strobe. Then we do one of two things. Sync. Do we need sync? Yeah, we do need sync. Oh no, sorry. I'm looking at the wrong line. M.if. So now we need to, on the sample point, we need to look at the previous bit and the current bit, and if they're the same, we need to keep counting. If they're not the same, we need to reset to 0. So we need two things here. We need a stable counter signal, and we need a last bit signal. And these, I think, need to be reset in the idle here. The last bit is always set to 1, and the counter is set to 0. Like that. So if the last bit is not equal self bus RXI, the stuff, no, we don't need all of that, so it's just stable counter equals 0, so that resets it. Stable counter, so if that is greater than or equal to 5, then we're in an error. I'm going to just copy that comment. I am going to make them into signals. Stuff error, so that we can at least assert them. How do we want to do this? I'm just gonna set it, I think. And it's never gonna get reset, at least not at the moment. And then else, otherwise, we increment. Now we need a little bit of logic to say when we can gate the strobe, the sample strobe. And that can be combinational, so that's cool. How are we going to do that? Because the gate is going to happen so we're going to get a sample strobe in at t equals 0. On that sample strobe here, we're going to look at this incoming bit, compare it with the last one, and if we determine that it is the same, at that point we then need to gate the next sample bit. I think that's right, isn't it? How did we handle resetting that previously? Oh, that happens there, okay. So if we got, for example, let's grab these comments. Sorry, I'm doing lots of thinking in my head at the moment. I will try and talk out loud. Okay, so here's the raw bits that we want to send, and then this is the stuffed bits that need to go on the line. And the same again for all ones, you need to stuff it with a 0. Now, if we were to receive a 0, that's all okay. So on the sample strobe, we look at the last bit, it was a 1, and a 0 is not a 1. Okay, so that's fine. So we then reset it to 0. Now, move on. So that's then going to have a stable count of 1, because it's going to go into this branch. 2, 3, 4, and then it's going to come and have a stable counter of 5 at this point. However, because a 1 is not equal to that the current bit, so sorry, the 0, which is the last bit, is not equal to the current bit, which is a 1, is going to reset it to 0. So I don't think we'll actually ever go into this branch here if we just look at the stuffed bits. If it's stuffed correctly. If it's not stuffed correctly, if there's if that is a 0 and it's invalid, then we will go into this branch, and that's important. So what I want to do is this stuff gate. I'm going to call it stuff gate, and that's going to be used to gate the signal in the module up. That is going to be equal to stable counter is equal to 5 or greater than equal 5. Because, so that's going to be 0, 1, 2, 3, 4, and then this one, oops, will be 5, and it can then gate the strobe. In the other module, we'll see this strobe still, so we will reset, and we will then no longer gate it. I think that works. I'm going to move that up here though, because that should be something that's always in effect. I'm going to put this somewhere else too. Okie dokie. How do we feel about that then? Does this want to go upside down? So if the bit is the same, I don't think so. I think that is the right way to handle that. Okay. Now in the can low level, we have the timing, but we now also have self.d stuff. And we give it the bus and self.timing. And that will then give us the gate that we've just produced based on the stuff sort of scheme. We need to wire it up. So M submodules the stuff. We also need to set what's it called? Combinational. So this stuff gate. Okay, we need a local signal, which is the sample strobe. Sample strobe. And that is going to be equal to the self.timing ANDed with the stuff gate. And it's actually ANDed with the inverse of the stuff gate. So I'm going to rewire this to be less than 5. There we go, so the logic is inverted. That then gives us sample strobe, which we can use directly here to sample the bits. Yeah, cool. So here, we just do sample strobe, get rid of this because it's no longer your job. These stuff is no longer your job. There we go. That's no longer your job. That's no longer relevant. Don't have that, do have this. Oh, okay, so we do need to do the pipeline. So that's kind of annoying. And I think that then will work. What do we think? No. Something can't be converted to nmygen, and that is on line 167. Self.timing dot sample strobe. These stuff Rx last. Oh, we can get rid of these. That's cool. Shift register. Okay. These stuff has no attribute bit. Oh, it's not bit. It's bus. Sorry. Bus bit. Yeah, that works. Work through the problems. Work through the problems. Oh, no. Yes, yes, no. Okay. What does the scope say? So we're getting some framing issues here, or at least the CRC is wrong. And that could be because the bit stuffing's not happening. Certainly the scope looks like it's not giving us much. On the red line, the blue line, yeah. So the blue line, I'm not sure if you can quite see it there, gives pulses, one pulse for each bit sample point. And what we actually want to do, the blue line is bit 8, pin 8, which is the debug SP. DBGSP. Oh, hello, stranger parts. Welcome, welcome. I was watching you while I was getting ready, actually. I think I was even hosting you, so welcome. How did everything go? I'm trying to remember what you were doing now. It was, oh, you're playing with the Rickroll M2 SSD thingy. Very good. So for everybody that's just joined, welcome. Please feel free to ask any questions or any sort of clarification or whatever that we're working on. You broke the scanning electron microscope. What? I didn't know you had one of them. Yeah, so we are currently playing with a Glasgow board, which is one of these. And I have produced this CAN add-on board here, which allows us to communicate with various industrial equipment, cars and other sensors, that kind of thing. So that's what we're working on, and we're just doing the gateware to receive a good frame and to handle things like bit stuffing and stuff as well. You just got it. Oh, that's such a shame. Was it sort of ready to break already? It's going back to maintenance. Should be back next week. That's good. Fingers crossed. Mr. Exquisite 93. Yes, we are using NMyGen. So this is Glasgow. Not sure if anyone here is familiar with it. There is a crowd supply campaign which is now finished, but I will put the link into the chat so that everyone can have a look. You can pre-order buy your own here. Glasgow is what they call a digital interface explorer. So you can write gateware, real-time logic that runs in an FPGA. And then interface with that from Python. So it's really simple to get going with a completely different interface. And to kind of prove the point a little bit, that's what we're doing here. So this is the Glasgow, and this is then the CAN add-on board. And CAN it's not a UART, it's not SPI, it's something quite different. So in one part you need to have a line driver, which deals with, if I show you the scope, it deals with the red and the green and yellow lines there. So there's this sort of semi-differential signaling. But also there's things like bit stuffing and various other things that are important. So what we can do then, because we have gateware, we're not just using a peripheral of a microcontroller, we're actually able to then sort of deal with this properly in real time. And then once we've verified things like the CRC, we can then push the packet up to the PC. So yeah, if you have any questions, please feel free to ask. Thank you everybody for all the follows. It's very good of you. Hopefully this is interesting and you learn some stuff, or tell me I'm doing things wrong, that kind of thing. Everything's welcome. Right, so back to it. I'm trying to remember what we were doing now. We were playing with so previously in the streams we have produced a sort of a big monolithic module which takes care of everything, and that's a bit yucky. So we've been breaking this big module out into one module which handles the timing, so that's when to sample the bit, and another module now which handles the destuffing, so that's when you can destuff. So here, for example, this is a frame on the CAN bus, and it looks kind of similar to the scope that I was showing earlier. Because CAN is designed for really robust communication in sort of harsh environments, so vehicles and industrial equipment like robot arms, that kind of thing, you want to be sure that you are sending the correct data, but also you need to be sure that you're not sort of asserting your state onto the bus and then preventing everyone else from communicating. So what you can do here, or what is done, is that after 5 bits of a given value, so in this case we've got 5 zeros in a row, if you were to keep putting your zeros on the bus, you're effectively blocking everyone else from communicating. So if you actually put a 0 on the bus for too long, the line driver, physically in the silicon, will then actually remove you from the bus and you no longer get to talk anymore. And to prevent that mechanism from firing, you actually then need to insert what's called a stuffed bit. So here, all of these pink bits are stuffed bits, and they prevent a length of, a run of too many zeros from setting the dominant state on the bus. So here you got 5 zeros followed by a stuffed bit, so you ignore that, and then you go back to your data. And then you've got 5 zeros followed by a stuffed bit, you ignore the stuffed bit, and then you go back to what you're doing. You've got 3 zeros, 1, so that's no stuffing required there. And then you got, again, 5 zeros and a stuffed bit. So handling this stuffing is kind of important. You can't obviously suck this data in off the line and then figure out that But you need to be aware of this stuffing so that you don't draw this data into your framing, because otherwise things like the payload length, so the DLC here is the data length control bit or bit field. If you don't handle stuffing, then that gets sort of placed in the wrong position on the frame. So yes, the issue we're having is now that we've teased out the destuff handling into its own module, it's not behaving correctly. And this is the output we're getting from Glasgow at the moment. It's just very simple. So down here, we are sending every 1 second, we're just sending the current timestamp, the Unix timestamp. And then over here, we see that incoming frame from the CAN bus. So the frame ID is 555, which is correct. And then 16, 15, 42, 30, 24, 42, is probably pretty close to what the time is. But if you watch this CRC valid flag here, it's invalid every time. No worries, thanks Scotty. It's good to see you playing with the Rickroll stuff earlier. I hope the microscope goes okay. Fingers crossed. Okay, so this is wrong, and why is this wrong is the next question. If I show you the scope, the blue trace that you can see there, it gives 1 pulse for every bit sample point. And referring back to this diagram here, obviously what we want to be doing is sample this one. Let me draw on it, I'll give you a better idea of what's going on. So we want to sample this one, and CAN actually samples it sort of slightly off center. So it's, UART, for example, would be about 50%. CAN is actually sort of further towards the back. And so we want to sample these bits, all of these, but we do not want to sample that stuffed bit. So what we're looking for on that blue trace is a spike missing when there is this stuff, if that makes sense. I'm glad to hear it'll be okay. Fingers crossed. Yeah, David, we did the CRC problem last week, but there's, as I was saying, the stuffing, there's such an interaction between the data on the line and the stuffed bits, and if you get any of this out of phase or out of alignment, then the CRC goes wrong. So you can see here, for example, the CRC actually has a stuffed bit in it, and if we're not handling that stuffing correctly, then it goes wonky and then it goes invalid. So yes, we are calculating the CRC now in Glasgow, but I suspect the issue is the stuffing, because that's what we're currently playing with. So what we want to do, I think, is look at the stuff gate and put that onto. So we've got 2 debug signals. The red and the blue line on the scope are debug signals that we're using. The red one denotes the duration of the frame, so it just sort of gives you a nice window around it. And the blue one currently is giving you every single sample point. And that is incorrect, because I don't think it should be giving you the stuffed sample points. So then, just reminding myself, debug SP is the name of the pin. And that's being set here to RX ready inside the CAN subtarget. So that's actually not right. We want to use the low level is one part, but then inside the low level we've got the timing and the D stuff. So we want the timing dot sample strobe. And that sample strobe will give us everything. So let's just review that quickly. Put the scope back on. Hopefully you can see the blue, the very short pulses, so they're a bit hard to see. There you go. So that's giving us every single sample point. Now let us put it onto where have I gone? Debug SP, here we go. So we don't want the sample strobe from the timing module anymore, we want the D stuff. And it was called, something about gating. Forgotten. Stuff gate, let's call it that. Stuff gate. And I think this is going to be incorrect. Let it build and run. Oh, no gating at all of the stuff bits. So that is wrong. The stuff gate at the moment is high constantly. Let's do less than 4. I feel like that could be the winning solution. No. Okay, maybe not. Let's do if it's greater than 0, just to see if we're actually counting any stuffs. Yeah, exactly, Omni. That's a good call. Signal. If you just give signal bracket, that will be a single bit width, I think. Okay, there we go. So we are counting. Oh, interesting. What are we counting there? Let's just zoom in on the scope. I'm going to go in. Oops, push the buttons. Yeah, so that gets to 1 and immediately resets. But then as soon as there's a length there, do you see towards the right hand side of the screen, there's a stable series of bits and it doesn't increment, or at least it goes back to 0. So I think we got something wrong there. Let's have a look, see. If the last bit is not equal to, oh, we're never setting the last bit. Don't. Okay. MD sync plus equals last bit equals self bus RXI. Okay. Let's see what that does. So hard crash, you're talking about stable counter equals a signal. Ooh, yes, that's a very good point. Thank you. I thought we did something about that. Never mind. So let's do range 6 in there so we can count up to at least 5. Looking at the scope, we do have the beginnings of what we're after now. So do you see it's counting up, but it's resetting itself again? And that is exactly something that your point there about a single bit width is going to potentially solve. So for that stable period, we should see it go high 1 bit after this beginning of it, and then it should stay high until it then changes again. There we go. Look at that. Cool. Thank you, Hard Crash. Now the issue is that so valid CRC, yes, is a very interesting point. You can see it here. Valid CRC, no. Valid CRC, yes. Yes. No. So that's just funny. Yeah. Real-time code review, indeed. Yeah, thank you. Wind this back out to show the whole frame. Okay. Okay. Now then. Yeah, so I've made that big enough to hold the values 0 to 5. I might actually make it just a 3-bit field so that it can go all the way up to 7. Now, the issue we've got at the moment is that we are not framing it correctly. So if I show you the scope again, you can see that red line continues way past the end of the frame. And that's incorrect. It goes a long way. There you go. And that could be for a number of reasons. Ooh. Well, sometimes it's in line and sometimes it carries on far too long. If we have a look at the output again, you can see here that we've got frame length 6, frame length 4, 7, 4. So we're expecting 5 in there all the time, always 5. The frame ID is also 289, which is incorrect. It should be 555. So I suspect we've got an issue with the sample point coming out incorrectly. Let us put something else on the frame. So I'm using CAN send at the very bottom here. And you give it an ID, so 1, 2, 3, and then a hash, and then some data. So 1, 2, 3, 4 would give it a 2-byte payload. And that then comes out as 684 and a 4-byte, and then look at all the Fs in there, and there's a 7FFFF CRC. So I think this is quite wrong, unfortunately. So the dstuff gate is going to handle where are we dealing with? Here it is. So the low level will have this sample strobe which is gated. So it's using the timings. This is the point at which you sample a bit, and it's then gating it with the stuff gate. The stuff gate is now wrong though, remember, because we set it to greater than 0, and that needs to be, I think it was less than 5, was it? To be correct. So let's just put that loop back on and rerun the application. Yeah, in the scope, you should only see a single stuff bit at a time. Okay, so now we're getting data, and we're getting good CRCs, and invalid CRC there. Okay, I think now that is actually a 4, not a 5. Just try all the magic numbers until it works. Simple. That looks better. Okay, so if you look at the scope now, we've got some stuff happening in the payload, in the frame. And if I cancel this and do our specific frame, there we go, we can craft it, and we've got stuff bits in there. If I now do something special, so I'm going to do a 0, payload, we should get lots of stuff bits. There we go. And they're working properly now, which is brilliant. Fence posts indeed, yeah, off by 1 and all that. It's also partly because of the pipelining in here. So we are counting to 5, so 0, 1, 2, 3, 4, and then the 5th one is killed, or is dropped. The issue is, though, that actually after the 4th, we need to disable that strobe so that the 5th one gets completely ignored. The strobe never ever gets through. And then after that stuff bit has happened, we can then start letting the strobe through again. So yes, it's 5 minus 1. Because we need to gate this strobe. And I think actually that we've got the timing in here, so the D stuff shouldn't give a gate to the interface, it should give a new strobe to the interface. So self.sample strobe stb. Let me count your zeros. So 0, 1, 2, 3. Yeah, so you've got 4 zeros and then a 1. That is valid data, and we can try that quickly if you like. This should still work. So you can see the scope. If I give a frame which is OF, that'll be 4 zeros followed by 4 ones. And you can see on the scope there that we have a stuff bit. Where's the stuff bit? Let's get rid of the data. Yeah, so that stuff bit is, I'll tell you what, let's do a 5, 5, and then an OF, and then a 5, 5, so we can frame it. There you go. So the 0F has no stuff bits, but if we make it a 0, 7, so that would be 5 zeros followed by 3 1s, we introduce a stuff bit, do you see? And if we make it a 0, 0, dot 0, 0, that will be 16 stuff bits in a row, and 16 divided by 5 is 3.2, so we should see 3 stuffs, I think, up here. There they are, 3 stuffs. Okay, so hopefully that kind of makes sense. You can play with it more if you'd like to sort of get a better feel for it. Yeah, cool. So that all works. Now we're going to rework this so it gives us new filtered strobe, because there's no point getting someone else to implement the filtered or the gated strobe for you. So this has to be self.timing.sample_strobe, and I'm going to call it sample gate, and the sample gate is going to be just a wire. Yes, that's not a bad idea. Just grab all of the previous commands. So the sample gate is going to be stable counters less than 4. And we're going to keep that explanation because that's a nice one. Pop it there. Okay, we can then get rid of the stuff gate. That's not relevant anymore. And we can then reword stuff gate to sample, you can't see that, sorry, sample strobe. And now we should only get those very thin blue spikes on sample points for bits that are not stuff bits. This is no longer correct, and actually we need to use self.bstuff.samplestrobe. Okay, how's that work? Move back. There you go, looking good. Cool. So you can see there, hopefully, the blue fuzz. It's very thin. I can turn the contrast up, actually. Let me do that. There you go. So if we send those test frames that we came up with just now, 55OF55, there's no stuffs. But if we send the other one, so 55000055, then not very easy to see, but there is a stuff bit in there. There are 2 stuff bits in there. It's quite a lot of noise on the line, unfortunately. Not going to work out. Hang on a second. They're kind of runts, aren't they? They're not actually. What am I trying to say? They're not gated properly. So that's problematic. So that there should be a stuff bit, I think. And you can see that little runt. So if I put a 0 1 in there, or let's do 5 5. Look, so that's a proper one. And that's a runt. No good. This is the problem with this kind of logic. What we actually need to do. No, I think this is a genuine issue, Omni, because it's kind of a metastability type thing, isn't it? In that the gate gets disabled at the same time as the strobe is strobing. We need to delay the disable of the gate by 1 clock cycle. And to do that, yeah, glitching, exactly. So to do that, I think what we're going to do is actually make it not combinational. This is not the one I want. D stuff is the one I want. I think we make it synchronous. Let's see what that does to that clock. That's that spike there. I think that will smush it. Oh. Oh no. Oh, why? Sample strobe. Oh. Let's make it synchronous but not in there. That's the stupid thing to have done, sorry. There we go. That's better. It's completely gone now. Okay, cool. Well spotted, whoever it was that came up with the idea of digging into that one. There we go. So there are our clear stuff bits. Much better. And if I put a 1 in there, we should lose one of those stuffs, or an F in there, sorry, we should lose one of those stuffs. We lose 2 of the stuffs actually. Let's put an 8 in there, we'll lose 1 of those stuffs. There you go, brilliant. Cool, much better, happy with that. I'm gonna have a quick drink. If anyone has questions or wants to point anything out or anything like that, please do feel free. Right, what have we actually changed now? We've got a new strobe which we're using correctly over here, which is good. Let's just try and make a quick commit. Timing on the idle. Did we do that? That is line 52-ish. This idle signal here. We did do that, yeah, okay. So that gets added. Does that get used? Timing to idle, it does get used in the D stuff. Okay, cool. Oops. What have we got here then? We've added the D stuff and we've pulled out all the D stuff into its own module. That's good. Nice. And then we're using the debug sample strobe, oh sorry, the D stuff sample strobe on the debug signal, which is also good. Cool. I suspect that the D stuff can be tidied up a little bit still, but I think that's good enough for right now. We still need to do the error handling, so if we have too many stuff bits in a row, but let's look at that later. So we've done the D stuff, which is cool. I now think we do need to shift this, or move this shift register out. So currently in the low level module here, we are pulling data into a shift register, which we're then presenting to the layer above to say, here are the last n bits we've received. Do what you will with them. And now that this low level module actually doesn't do anything else aside from that, it's probably okay to leave it, I think. So this low level module takes care of requesting that the timing module continues running and sucking in data into the shift register to share with the upper level. And I think that's okay. The issue we have now is that this RX ready signal because of the pipelining, needs to happen one cycle after strobe. Currently we're dealing with that by putting it into its own state, which is a bit icky. And if we can avoid that, that might be nice. So perhaps we go for so I'm kind of doing like a latch there. So if the strobe is active, shift the data in. Else if the strobe is not active implicitly, but sample strobe previous is active, then we can poke the RX ready. And then else if the boundary strobe is asserted, we can then do that bit. Well, that's nicer, isn't it? We can then change setup for run. And we can then get rid of this final thing. So this is then going to be if that and the boundary strobe and the timing is no longer running, then return to idle. Oh, better. Okay, how does that look? Does it work? That looks good. Yeah, stable data, stable CRCs. Awesome. Let's call it delay, actually. Now then, what else do we do here? So when we're in the idle state, we are clearing the shift register, which I think is important to be doing. Who is responsible for setting timing.run though? Because I feel like that is another thing we can do. We could potentially get rid of this entire state machine. Timing.run here is set by who? So this is a request to continue running the timing module. So it will start itself on the first dominant state of the bus. So that's the very beginning of the frame. And that will then keep running until someone says, okay, you can stop now. That okay, you can stop now comes from all the way up here. CRC run. CRC run. Where does it come from? It comes from somewhere because it is stopping. Ah, here it is. Okay. So that's set. Okay, so when we return to idle, you let the timing module stop. That's good. That means that as soon as we are no longer in idle, so as soon as that RX trigger happens, we are asserting the run flag. And because of that, we can put a thing on the front of this. So with if not self.timing.run, we can clear the Rx data to zeros. We can then do an elif. We get the sample strobe. Then you can shift the next bit in. If the delay is then active, we can let the people up above know. Go for it. Look at the Rx data. And then if we get the boundary strobe, we don't even need to care about that anymore. I think we can. This is scary, but I think we can do that. Oh, that's much better. Is that correct? I feel like we've got some wires going a bit all over the place, and that's not so nice, but we'll look, see. Oh, yes. Brilliant. That looks good. I need to turn the intensity down on those signals. They look really weird. Okay. Oh no! I turned the scope off. Oh, I'm up it. Coming back on. It'll take a while to boot though. Okay. That's very nice. This RX ready is important because it tells you to look at the data. RX ready, we're always dead now, that's not a thing. RX data is ready, that's good. Remove this, I'll move it out of the model. No, I think that stays in this module. And I think 32 bits is quite a lot, but we can... Let me just turn the intensity down again, must have lost it. Okay. Okay. I think 32 bits is quite a lot, but let's leave it at that for the moment. We've then got the timing and the D stuff. Of the two, which are used here, timing and D stuff, they're both used, okay. Would it make more sense to actually provide these signals? We use the sample strobe from the D stuff and the timing.run. Yes, it would, okay. So the issue now I'm trying to avoid is the spaghetti of like how to connect all these modules together. I think it's called that, yeah. Do we actually need bus at all? We do need bus because that's the RX signal. Okay, so actually what we need is RxD. We need the run signal, sample strobe signal. We don't need anything else. We can put those into here now, RxD, run and sample strobe. The bus is then going to be taking care of the level up. And that's going to be here. Okay. So the low level ends up getting bus dot RXI. Let's call it RXI here for consistency. It gets, what else? It gets the run signal from timing.run, and it gets the dstuff sample strobe. Okay. And it then produces us with a ready strobe. Alright, so I'm going to call that RX strobe. Okay, so it provides us with a data and a strobe to look at that data. Get rid of these two. That is what? Oh, that's fine. That's now self.sample strobe. Self.sample strobe. Let's get rid of, yeah, that's cool. And then this is no longer self plus RXI, it's just self RXI. Cool, okay. Is that going to work? Who knows? No, it doesn't work. No attribute D stuff. Line 222. Oh, okay, low level D stuff. So that's actually now just D stuff. Now we've got no timing, which comes from 2, 3, 4. Okay, so that's just low level, it's just timing dot. These are kind of debug signals, I think. 2, 4, 4. Yeah. Low level RX ready is no longer that. It's low level. Hang on, sorry, what? 250. Oh, there we go. So it's now called something slightly different. It's called data strobe, RX strobe. That's TB. Okay, so we need to rename all of these to the end of the module. RX ready. RX strobe. No attribute timing 164. Oh, so much to tidy up. So it's no longer timing to run, it's just run. Now RX ready 187 again. This is no longer RX ready, it is STB strobe. Come on. 188. Oh, okay. So the CRC module is trying to look at. Okay, it's trying to look at the most recent bit that's still on the wire. So because it's all synchronous, it's not the bit that's in the shift register already. Ah, no, it is the bit that's in the shift register because we handled that delay. So we can just do low level the RX data 0. That's cool. That should work. Fingers crossed. Okay. And my agenda building. Oh, valid, valid, valid. Yes. Look at that. Cool. Okay. Just to show the scope as well. So we've still got the occasional bit stuffing coming in there. It's random data, so well, it's not random data, it's the timestamp. But we can try with something else which we know has some stuffed bits. There you go. And something which we know has no stuffed bits still. That. Nice. Okay. The new bit. Next out. Oh yes, I remember. This is the stuff we did, I think, last week, was it? So this is grabbing low level as a module for the RX strobe and the RX data. That's fine. Yeah, happy with that. Okay. What else can we do? Yeah, all of these. This is cleaning up and low level. Again. Okay, that's much nicer. It's, yeah, teeny wee compared to what it used to be. It's now got the line from, you know, the wire from the bus. It's got the run flag and the sample strobe. And it uses that all correctly. The stuff module possibly could look at a bit of fix up. Timing module is pretty good, I think. The baud rate stuff needs to be pulled out and put somewhere else, but that's okay. Wondering if we can get rid of the state machine on this as well. Because we got this run flag, which is putting us back to idle. Let's think about that and come back to it maybe. But the important thing is that this gets the the bus, which actually we don't need all of, we can just do RXI, so that'd be nice. And this is actually the inverse of RXI. So it's not can low, it's can high. And the reason we do that is because we trigger on it. Or a high rising edge for trigger. Okay, that's cool. Let's keep that on. The D stuff is good. From the D stuff we get bus and timing, and I don't think that's probably correct. The bus, we only need RXI again, and timing, we need the sample strobe and the idle. So we can just clean that up quickly. Oh, hang on, sorry, we never finished cleaning up this. Can timing. That doesn't need bus, it needs bus RXI. There we go. So D stuff needs bus RXI. Oops. Will TX need the bus for CAN timing in the future? Yes, it will. So on transmit, you change your signal. Well, AX as well. That's a good point, actually. Yeah. So the timing module, the CAN timing module, gives us the sample point and the bit, or the bit boundary. If that makes sense. So if I show you the Wikipedia diagram again, so the CAN timing gives us this point here, which is the bit boundary. So that's when you change your data on the line. It gives us the sample point, and then it gives us the next bit boundary, and then that repeats. So the ACK is a level up from the CAN timing module. D stuff only cares about receive. However, we will need a stuff module, which tells us when to stuff a bit and not shift out another bit, if we're trying to do transmit. And in terms of things like ACK, then that is handled, I think, at this level here, the CAN sub-target level, at the moment at least. So I think we can get rid of all of these signals in the lower levels, which is nice. Do that. And then the timing for the CAN-D stuff, we use idle and the sample strobe. So it might be sensible just to leave all of that in there. I really can't decide actually between giving a specific signal from the bus and just the entire bus. I guess it makes sense to give the entire bus because then you're sort of floating the objects around instead of signals, aren't you? And now I'm going backwards and forwards here, apologies. CAN timing then wants that back as well. And then the interface becomes a bit cleaner. Oh, yeah, it will do. Excuse me. All of these are wires, so whenever you have a signal which is then assigned in a synchronous fashion, so m.d.sync, that becomes a register. But any m.d.com or anything else where you're just passing a signal around, it's just a wire effectively. So that's quite nice. Or at least that's my understanding. So that means that CAN low level probably also wants to have the whole bus as well, even though I've just undone that. CAN low level, that's probably remove the missing RXK. RXI, so missed removing RXI. Oh no, here we actually want it, but oh, you're right. Yes, thank you. Here it does need to go away. I wasn't thinking when I did that. Clearly. So let's just make sure it still runs. Looks good. And we have a couple of stuffs coming through as well, so that's good. Yeah. Cool. It's 122, it is. Yeah. Right, where were we? We were here. The low level, the CAN CRC just gets the low level. Is that correct? Low level module, and from that you get the RX strobe and the RX data. That's fine, I think, yes. So the sub-target gets, it creates the bus, CAN bus pads. I don't think, why would we do that? Why would we put the CAN bus at that level? I don't know. Let's not do that. Rework this to be bus equals self.pads, self.pads. Okay. Oops. I think that's quite clean now. Compared to how it was, it's a lot better. That still works, it's good. We've still got some stuffs and things coming through and it's still valid. That's nice, cool. Okay, I think now we're at the level where you can actually look at the higher level stuff and sort of start reasoning about that better. And what I meant to say is I think we're at the point where we can do this. So let us take a commit of that. General cleanup, and let's have a look. Now, previously we tried to work in an ACK and it went horribly wrong. And this state machine up here deals with the framing of the data, the various fields in the frame. The arbitration ID is 11 bits. You got a remote request, you got the extended ID, and then you got a reserved bit. Then you got 4 length bits, and then you got n times 8 data bits. And then you got 15 CRC delimiter, and then the acknowledge slot. Now, from previously, we are retrieving the ID, the frame ID, in its entirety, and then we are retrieving the frame ID goes up to the host as 2 bytes. The arbitration control field, that's this bit, possibly even including the remote request flag, that goes up as another byte. And then we have the data, and then we have the CRC, and then there's the CRC-1, which takes care of, what does that take care of? Oh, that just takes care of the sort of the pipelining, I think. Oh no, the CRC1 takes care of sharing with the host the validity of the CRC we just received, because we're calculating it in the FPGA. And then we get idle wait as 2 steps, so the initialization of it and then the actual wait. And we wait for 8-bit times. Oops, 8-bit times. Now, currently, I think the 8-bit times we're waiting are after the end of the CRC. We wait 8-bit times. So we go 1, 2, 3, 4, 5, 6. Ooh, nasty highlight. do one of these again. So what we do is, I think we go from the end of the CRC, and we go 1, 2, 3, 4, 5, 6, 7, 8. And I think at this point, so halfway through the end of frame delimiter, we stop watching the frame. I'm not sure that's correct. Well, I'm fairly certain it's not correct, because I think this is something to do with the error handling. So first of all, the end of frame delimiter is lots and lots of ones in a row, and that's technically an illegal state. I think also people can start stamping on that if they see errors on the bus. So they can say, I think that's what we were looking at earlier in terms of the error frame. Superposition of error flags. I have a feeling that's where they go, in sort of here-ish. But anyway, either way, we should be waiting at least until this point, and we should also deal with the acknowledgement as well. So if the CRC is good, we should try and assert and acknowledge, and we should then wait until the end of the frame. Now, what we get is, I'm going to move this onto the screen, apologies. But what we get is the CRC is 15 bits. We then share that with the host, which is effectively no time. And then we get an idle wait. Now, what we should actually see is the CRC delimiter followed by the ACK. So ACK. And then we get the ACK delimiter. Oops. And then we get the end of frame, and I'm going to rename that from idle wait init to end of frame. End of frame. And the end of frame is 7 bits. So we need to make this 6 because it's 7 minus 1. We also need to only advance state on the RX strobe. Oops. And in the ACK state, we can now transmit the acknowledgement, or at least try. I wonder if we might be a little bit off to begin with. That is on what pin? It's on the transmit pin, and it shouldn't really go here for now, but it can. So it's going to be bus.txo equals 1. No, it's not going to be 1. It's going to be CRC out equals 0. That may be upside down. I want to transmit a 0. Oh, I hate this. Let's look up the datasheet quickly. What is it? It's a TCAN something. TCAN 501. 1051, sorry. So the transmit line here, dominant timeout is what I was talking about earlier, how it removes you from the bus entirely if you're sort of sitting talking for too long. The transmit low for dominant and high for recessive. So that should be high by default, and we should set it low when we want to send. So so it is reset to 1, and then here we should reset it to low. So if CRC out is equal to 0, we should say if it's not equal to 0. Okay, we see what happens. Let's scope up. Now I've got another node on the bus, and that will be doing the axe at the moment, but I can remove it easily enough. There's an error here, and it says idle weight in it is referenced but not defined. Ah, okay. It's not actually idle. Idle weight, here it is. This is illegal. Let's just go back to idle. And that covers all of that, okay. How are we doing then? Oh, data. Okay, but look at the scope. That is not a happy scope. Why not? Did I do MD sync? No, I didn't. So the ACK is still combinational, which means it should remove itself. Let's have a closer look at this. I'm just going to remove some pictures there so you can see the errors coming through. So if I zoom in on that end bit, oh, there's loads of frames coming through. And you can see that there's actually two states there. So there's the, I think, oh dear. I think I can also hear my other computer complaining about it because it's getting so many messages in, maybe? Maybe not. I don't know who's complaining actually. Let's do Glasgow safe. And that should let someone else, there we go. So someone else acknowledged it and it's gone off the bus now. If I transmit a frame, that's where the ACK should be. Oh, it's... If I do can send, can 0, 1, 2, 3, and then 5, 5, 5, 5. Okay, let's hone in on the ACK there. And that's approximately then centered on the graticule so that we know where it should be. And that is the graticule below no text along the top. So if I send frames, then that ACK, do you see how the ACK is kind of shifting slightly in respect to the data on the left-hand side? The TX ACK will affect the RX-in, yes, because of how the transceiver works with the line driver. So I just want to quickly show you this, if I may. So, so here, can you see my cursor, hopefully, is the acknowledge signal. And that is being done by a different node on the bus to this, which is at the end of the data. So one node is transmitting this, and then another node comes in and puts the ACK on. And if we send data, sleep for like 100 milliseconds. If we send data, do you see how that's wiggling around? It's not rock solid. That's quite interesting. So that's because the timing between the two nodes isn't perfect. Okay. So now, if we put Glasgow back on the line, what happens to that ACK? It's going to go into that nasty, horrible state again, I think. There. Oh, yeah, okay. We do, yeah, as far as Glasgow is concerned, everything looks good. But as far as the scope is concerned, everything looks not good. And that ACK is really horrible. I'm just going to send one frame. and we get that. Oh, okay, I know the problem. So the ACK here is actually being triggered on the sample points, not on the bit boundary, which is the issue we've got. So we don't want RX strobe, we want, oh no, okay, this is the point where we now need to look at another module to get the date, or the trigger we're after. Because we want the timing module to see the boundary strobe. So timing, boundary strobe, STB, yeah. And then we do that again here. Let's get Glasgow up and running again. And then pop. Oh no, even worse. That is horrible. I think Glasgow's being really naughty on the bus. Safe. And then someone else acknowledges it and it goes quiet again. Alright, that's what we expect to see. Omni, you say, when transmitting normally for the arbitration section, you are supposed to listen to the bus while sending, and if it isn't the bit you intended, you need to stop transmitting. Yeah, that's correct, yeah. Because we are just receiving at the moment, we're not too bothered about that, but I think that's probably in response to hard crash in terms of transmitting and hearing the receive as well, is that right? Now, I wonder if we need another one of these in here, another bit boundary, if we're just one bit too early. I don't want to go into safe, I want to go into can sniff. Yeah. So multiple nodes can potentially acknowledge a message at once, but a sort of a dominant on top of a dominant is fine. Equally recessive on top of recessive is fine. It's kind of like I2C with open drain, that kind of thing. Right, so if we send a frame, what happened? Oh, it worked. Apart from it came through a zillion times, look. And it came through wrong a zillion times as well. Well, I mean, we're kind of getting there. Maybe. Do you see as well, actually, let's have a quick look at that. So the shape of that acknowledge is funny. Do you see how it's got sort of a number of states to it? Let me do one of them. So if I bring you over here, can I zoom in on this? No, but I can copy it into Paint, and then I can zoom in on Paint. So this line here is the acknowledge, and we get, this is the recessive state, and then this is the recessive state on the other end. And here we have the dominant state from the originating node. But here we've got one state here, and then there's a little step up, and then there's another step down, and then there's return. So we've got this kind of, I'm exaggerating it, but yeah, like that. And I think that's because two people are driving the line between these lines here. So two people are driving it, and only one person is driving it. So one here, two here, and one here. And I think you'll find that Glasgow is driving it here, and the correct or the well-behaved node is driving it here. So yeah, our timing's a little bit off, and I think actually this looks a lot like, so here is the sample point, and here is the sample point. So I think if we have a look at the bit boundaries and just see where they lie, these sample points do actually look very central to the bit, don't they? Your thoughts? Debug. set to the TX assert yes, and remove the other node. So if we remove the other node, because this, the tool I'm using at the moment, which is this chap on the desk, is not very well behaved. If nobody acknowledges his message, it just sits there transmitting over and over again. It's like, please, will someone respond to me? That's not very well behaved. So I can remove the other device, or the other system from the bus, but I need to get it back on the bus again fairly quickly to sort of make the bus return to idle, if that makes sense. But certainly I think, let's just confirm that these points are the sample points, and let's confirm that the bit boundaries actually lie sort of where we expect them to, because I think at the moment they're shifted, look, and that would actually make a lot of sense in terms of, do you see, so what am I trying to say? What we have, let me get another color, let's do green. I think the bit time is something like that, as far as Glasgow is concerned. But if you look at where the act's been placed and where this is placed with respect to Glasgow's sample point, they don't line up. So this is actually the bit time on the bus. Sample point should be more like here, but I think Glasgow's seeing the bit time as more like this, which is a bit interesting. So let's add that to the red trace, I think. Let's just get this. Yeah, exactly. Let's put the bit boundary on there. I think currently the what was it? The bit sample point is on the debug line. Remind myself what it's called. Debug SP. I don't know why I called debug SP and debug arb, but I did. The debug SP is not used. Debug arb. Oh, hang on there. Like debug arb, but they got pin prefix or minus underscore t suffix. So debug arb is on the red line, and that denotes the frame. So we can rewire that to md combinational self adds debug arb t out equals, and let's do timing dot boundary stb, and the debug sp is here. Is the, yeah, that's already the, that's the de-stuff sample strobe, so that won't see the stuffed bits. That's fine. Hello, Alan. Good to see you. Thanks for joining us. Debug arb underscore t. What? Oh, I spelled it wrong. Debug arb. Oh no! I can't spell boundary now. Boundary. I left out the N again. Here we go. Okay, one frame. Watch the scope. Interesting. Now, oh, hang on. Let's turn off our acknowledge as well. I don't want to see that at the moment, because that's interfering with stuff, isn't it? So the acknowledge should be a dominant state surrounded by recessive, so that gives us a single bit time, and that would be good to see. And that is there. Interesting. Look at how out of phase that is with Glasgow's idea of a bit time. I wonder, is this can't be drift from just the duration of the frame, can it? I think it might be. Well, that's really upsetting. Do we need to use a PLL to get some faster clocks going on here? Let's get 2 bits per graticule. Oops, always go the wrong way when I got zoom turned on. There you go. That's approximately 2 bits per graticule, isn't it? Okay. So they're all lined up reasonably nicely at the beginning. Still looking good. And then here, no, it's still good. Good. Now you can see it starts to shift away. You get the noisy spikes. Shifts quite a lot actually, look. That's just over the duration of one frame. Okay. I wonder if our 19 is just not right. Yeah, we are too short. Yeah. So let's do our calculations quickly. We've got in the low level module here, Python. So we've got that, and the quanta, we've got 10 quantas per bit, oh yeah, bit time. And then we've got this one here, platform. Oh, okay, so I need to rework that. So it's 48E6 divided by quanta. And that gives us 19.2. Yeah, so if we're counting only 19 instead of 19.2, what's that? That's 19 out of 19.2 is like -1%. That doesn't sound too bad. The 2 does add up, yeah, but I'm surprised it adds up so much, because UARTs, for example, are quite good at, oh, I suppose UART is over an individual character, it's not over an entire frame. Yeah, that's a very reasonable point there, actually. Okay, so I think we need a faster clock. Let's see if we can steal some code from another module. I think video VGA. I think that uses a PLL. There it is. Pixel clock frequency, and that is what? That's set to 12 megahertz. Oh, sorry, 25 megahertz. I wonder if we can get much higher than the 48. Let's give it a go. Gateway.pll. So, oh, we got the UART in here for some reason. Wonder why. Okay. How does this work then? We can give F out arbitrarily by the looks of it, and then you can add a clock constraint saying, how does this work? Pixel clock freak. Okay. Yeah. And that then puts it in the pixel clock domain. So, yeah, I think that might be a good idea. So we've got 250 bits per second, kbits per second, sorry. Times that by 10 for our time quanta, 2.5 megahertz. So we could go for 2.5 megahertz out of the PLL potentially. Or 5 megahertz or something similar. And that would then be a 1-to-1 clock ratio, or like a 2-to-1 or whatever. So that might be a good idea. I think there's also some way to determine what kind of error there's going to be. I don't remember where that was though. I don't think it's on the PLL. I wonder if the PLL is precise enough. Because look here, we've got 25.175 megahertz. That's kind of, that's quite nice, isn't it? And the clock constraint here, I don't know what kind of constraint that actually applies. Need time to do actions between states. Yes. Now, so let's look at this. The CAN timing module. So this is the module which I'm proposing putting the ELL into, and I don't think anyone else. No, they do care about it, don't they? Because they've got to synchronize to it. Everybody cares about it. Okay. Let's aim for a 50 megahertz clock and see what happens. We need to put that somewhere quite close to the top then, I think, don't we? Like here. And then everyone else has got to be able to use it. I don't know how that crosses modules, platform, add clock constraint. So if I had a PLL here, do we think we'll be able to use CD picks everywhere else? Or will I need to pass it through? There are a couple of places, Omni, where I do stuff between the bit triggers. And the other point, actually, as well, that's interesting, is that the beginning of the frame is not going to be synchronized to a clock. So unless I can gate the clock and release that at the beginning of the frame, such that the clock starts up perfectly immediately, I do need it to be a multiple. I can't have it at the same frequency. I definitely can't have it slow, I don't think, as well, because then you start missing bits. Yeah, so let's just go for this, see what happens. Grab this as a reference. I'm going to put it up here. And I'm going to call it, not pix, but bit. Why not? And let's do self.bit clock frequency equals 100 megahertz, do you reckon? Oh, slower than 48 megahertz is okay. Okay. Sorry, I thought you were saying slower than the bit time. I was a bit confused. Okay, let's go for 50 then. Yeah, exactly. The 25 would be 10 times faster. 50 would be 20 times. Let us see what that does. I think it might just blow up immediately. Does not exist in design, ignoring clock constraint. Bit clock does not exist in design. Is that because nobody uses it? So I need to do MD sync needs to change out for MD pix, I think. Yeah. Oops. MD sync swaps out for MD, well, not pix, but bit. Let's just do everything. Oops. Get away. Oh, that seemed okay, didn't it? Didn't complain about it, and it's using it in the modules as well. So let's see. Oh no. Oh, this is because we're still using the wrong base for our calculations here. We're not using platform default clock frequency. Oh, wait, sorry, we are using platform default clock frequency, which we shouldn't be doing. We should be using instead the new clock frequency, which is, don't remember, 25 megahertz, I think it was. Yes. I'm just going to type it in. 25E6. Not sure if the ICE 40 PLLs have the good delay adjust. You could just use to sync the clock up to the bit edge. Yeah, I don't know. But the other thing as well, don't forget, is that the frames can come in arbitrarily. It's not like you lock on to a standing signal, for example. Oh, that's really, really walking fast, isn't it? Look at that. Let's do multiple. Sleep 0.1, so 100 milliseconds between-ish. You can see that that is then walking and drifting quite fast. Yeah, we only get one start bit. And it's not necessarily bounded on both ends as well. So it's got like an edge on one side, but possibly not an edge on the other side. I'm going to turn this 25 megahertz up. I'm going to turn it up to 100. And I'm going to see what happens. I'm also going to print out this bit psych and just see what it comes out as. I'm going to see what that comes out as, and I'm going to see what this comes out as too. Alternator method. Can you alternate the count up and down by 1? Yeah, so that's... Oh, okay, this is a perfect 10. And it's still drifting. Oh no, hang on. Ah. Failed at 100 megahertz. Okay. We can get 70... So what do we need? 2.5 megahertz out of 90-ish. So, what, 85 divided by 2.5? Be 34. Let's do 85 then. 85 megahertz, and this needs to change as well. 85, and this needs to change. Might make it a global in a sec. So yeah, some of the UARTs in various devices give you the ability to wiggle, just like that, to sort of modulate effectively the clock. In case that's still not happy. So previously we had 19.2, I think, which means that for every 5 bits you have to skip a cycle to keep it in line. So you do, or add a cycle, sorry. So 19, 19, 19, 19, 19, 20, and then repeat. By resetting the counter on state changes. Yeah, that's an interesting point. So doing an edge detect and resetting the counter there. Yeah, okay, I like that. I think this PLL approach is not going to work out, is it? Just undo all of the stuff we did. Well, it's not going to be as helpful as we hoped it might be. Thanks, Hard Crash. Yeah, so what we can do is in the CAN timing module here, we can permit it to skip this if an edge comes in before that happens, I think. And edge is coming quite regularly actually because of the bit stuffing, as you say, yeah. You can guarantee that an edge will be present within at least 6 bits. Okay. So it might be worth having another state in here again. How are we going to calculate this? I'm going to print these out. I'm going to print that. and I'm going to print bitsake as well. That gives 19.2 versus 19. So for every 5, no, okay, let's ignore that. If you are past the sample point and an edge occurs, reset. I think that's how we do it. So if there's an edge, or we reach the end of the period, then reset. Yeah. And we define an edge by what? We can copy what we're using in the D stuff. So an edge is just where the current signal is not the same as the previous signal. Does that work? Yes, it does work. And we can do that on the 48 megahertz clock. So we have last bit signal, and we have last bit equals. Do we have the whole bus here? Yes, we do. Oh, we've actually got the RX trigger, so we can just use that self.rx trigger. And then edge equals self.rx trigger XOR last bit. Does that work? Is that an edge detect there? Yes, that is an edge detect there. Oh, look at that. That's much better. We are getting garbage though. So, why are we getting garbage? Have a look at the scope. It looks like there might be a couple of edges coming through. And I wonder if... Oh, hang on. Yeah, okay. So what we need to do, edge is only permitted once we have passed the setup cycle, and it's only permitted once as well. I don't think it's permitted multiple times, which it currently would be. So that captures an edge. And then let's do a edge cut. Is going to be counter greater than bit setup psych and edge. Work? Yes, because as soon as that resets it to 0, it's no longer going to be valid anymore. No, that's not happy still. You can really see that back wobbling around now. Quite interesting. I love seeing that kind of thing. So this is claiming that CRC is valid, but it's really not getting good data, is it? I think I might want to put the edge cut onto a signal so we can see when it happens. Maybe. Looking at that waveform. It's still out of phase. It's not actually updating as I'd hoped it would be. Or falling in phase, or whatever you want to call it. So let's do Glasgow safe again. So that just sets Glasgow to do nothing. And let's then send one frame, which somebody else acknowledges. There it is. Okay, if we then turn Glasgow back on, interesting, it doesn't join the bus cleanly. That's interesting. Now we send one frame. Let's just scroll all the way over again to the beginning of the frame, see if it's in lining. So that looks pretty good at the beginning of the frame. Is our issue that we are... Yeah, okay, so the issue now is that we chose 19 when we should have chosen 19.2, which means that we are running too fast and we never get the ability to use our nice shiny new algorithm to realign on a clock edge. So if we choose ceiling instead of rounding, then that will allow this to become an interactive part. So that should give us 20. Oh, sorry, you didn't see what I changed there. I put, instead of doing round on the calculation, I use math.ceil. And that should give us 20 instead of 19, which it does. And now if we do a transmit, it's ever so slightly delayed, isn't it? But it's now much more in phase than it was before. So we're permitting it to run a little bit slowly. And as soon as there's an edge, we then bring it back into alignment. Do we bring it? Yeah, exactly, yeah. And it will be bounded by the 6-bit restriction that we talked about earlier, because of the bit stuffing. I wonder if we can get, if you look at the scope, there's, do you see how, let's just zoom in on that. So the edge there happens, and that's probably a 48 megahertz clock between here and here. Oh, it's not. It's only 7 megahertz. Unexpected. Although don't forget there's going to be some rising edge stuff. I wonder if we can get it closer is what I'm trying to think. Or if it's even necessary to worry about that slight offset. We do track it pretty well. Let's have a quick look. What can we do about that? Right, yes, I like it. Resetting it to 1? No, hang on. If we no, because yeah, that will be always late, wouldn't it? I wanted it to be a bit quicker than that though. So where are we? We're in the timing module. And we want to say if the edge cut happens, edge cut is seen by counter is greater than the setup and edge. Edge is seen by the trigger XORed the last bit. So that should happen immediately in inverted commas. That shouldn't be delayed by 1 cycle. That should happen as soon as the RX trigger or the input signal changes. And we are in range. But then this section here won't happen until the next 48 megahertz clock comes around. Maybe we leave it. Maybe that's okay. It's pretty good. It tracks that edge quite nicely. It will bound our error. Oh, but we're still not getting good data in. That's annoying. frame ID 101. Otherwise, you could use the edge to measure the error and adjust your counter compare value. Yeah. I think what we've got is a good solution at the moment, in that we let ourselves run too slowly and we bring ourselves back in line on every edge. I think that's kind of a simple and optimal approach. The issue I really wanted to get rid of was this delay that I'm showing on the scope at the moment between the edge and us then acknowledging it, but I think that's inevitable and impossible to fix up. It's a little bit longer than I'd hoped, but I don't know the propagation through the CAN driver and things, so, or the transceiver. So it might be that yeah, it's not our fault as such in the FPGA. It might be that it's the transceiver, the line driver. In terms of what we're doing now, then we should be able to get, so the edge cat's cool, that works nicely. Let's just smoosh it up a bit. Let's restart that just to prove it out. Okay, the issue now is that we've got rubbish data coming in. Like that. Oh, hang on. Did you see that? At the top, we had a 1, 2, 3, 5, 5, 5, 5 with a CRC that's valid. And then we had this, which is not cool, and I don't know why it was there. And 1 frame. You get 1 frame. Zoom in on it. Oop. That is what we'd expect. There's a lot of noise in here because I'm doing really lazy probing. Oh, and I'm also playing it very slowly. I was wondering about resets and sort of coming around and starting again. Let's have a look at what we've changed. We have changed the. Okay, let's do a nice commit of just the changes relevant to the the error handling. That and that. Not this. Not this. Not this. Okay, so that takes care of the error in the bit time. Handle bit time error. Let's stash this, run it, and see if we still get the rubbish. We do not. Okay, so our problem is now in the stash. Could well be in that handling of that ACK. Get rid of that, don't want that. Okay. Oops. Reload. Okay, so the timing is now good. I'm happy with that. It looks like it's keeping its alignment nicely. D stuff, low level, sub target, here we go. And this is where the ACK is being handled, and I think this is where the issue is being introduced. So we could actually stash just that series of extra states. Not this. Yes, this. Yes, this. Oh, there's nothing else in the diff. Okay. Okay, never mind. Why can't I pop that? Make changes or stash them before I merge. I do not want to do that. Yes, I want to rewrite it. Okay. So I think it is our handling here. And the return to idle, possibly. Which for some reason is giving us 10101010. If you look at that. Yeah, so the data is literally 1010101010101010, and that's wrong. The scope looks correct though. I wonder why it's wrong. Let's just do the date. This is the timestamp coming through every 1 second. And you can see that the timestamp is there, and there's all this rubbish around it. So if we zoom in on the app again, the app's going to be moving around because we've got dynamic data now. But there's the edges. They look okay, don't they? A little bit wiggly, but that's alright. There's a runt there. Do you see it? That's way too close to the end of the frame, isn't it? Oh, maybe not. Or the end of the bit, sorry, not the frame. Maybe it's not a runt at all. What's going on? Okay. We can put our rack in again, see where it comes. This is a 5-byte payload. That's the ACK on screen there, wiggling around with respect to the transmitter. Let's put our ACK in. Restart Glasgow. I don't think this would help. I don't know why it would. No. Although it does seem to be nicely behaved now. And look, we are well in line. That's good. Some space. Print out a message. Yeah, that's wrong. That's really wrong. Can you plot where it thinks the frame starts and ends again? Yep, we can do that. I think it's down here, isn't it? On the arb. Make it idle. Let's just get rid of that zoom. So this should be on red, I think, now. And okay, because what is it? Because we are still running for the end of frame, should we stop immediately instead of doing that? I think this is just padding. I'm not sure if we really need to watch it right now. So we've got the CRC delimiter, the ACK, and then the ACK delimiter. And here, idle. Let's go to idle. That should wrap it right up against that ACK. Which it does, but we still get loads of rubbish, look. There. You get an entire frame. This is not actually a frame. This is trying to reason about this. Okay, let's just do a quick run. One frame, close, and then scroll up. Okay, so 1, 2, 3, 5, 5, CRC valid frame. And that matches what we see on the scope, which is a CRC of 2, 3, 6, 3. Yes. And then we immediately see these other bits here, which is incorrect. So if we send 2 frames, 1, 2, and then scroll up, we see 1, 2, 3, 5, 5, 2, 3, 6, 3, garbage, and then we see frame 101, 3, 01, 5, 5, 2, 3, 6. Yeah, look. There's rubbish in the FIFO. Coming from where? Where is it coming from? Who put stuff in the FIFO? I think it's only this one, this module. Yeah, it is just this module. And it gives a series of data into the FIFO. We get the arbitration ID, 2 bytes of it. We get the arbitration control, 7 bits worth. The data, 10 bytes worth. Then we get the CRC, 2 bytes worth, or 15 bits, sorry. And then we get the CRC valid marker. So if we have a look at the actual, whatever you want to call it here, the interact doodad, let's break it off and let's just read. We're calling it UART, that's why we're dealing with UART in the header, in the import. Don't know why. Yeah. Read 1 byte. Print that byte out. Okay. The routine is not subscriptable. Okay, so if we send our frame, ooh, we get loads and loads of 1s. There's our frame, and then there's loads of 1s after it. Who is responsible for giving those 1s? I bet you it's this. If I put OX42 in there, because 42 and all that, I reckon these will be 42 hex, which is something decimal. Yeah. Oh, we've got millions of calculators already, don't need more. Okay. 42 hex is 66 decimal. Boink, there they are. That is exactly the problem. We are not advancing out of that state. Until then! Oh no, you're an idiot, Atty! I put in, do you remember? I put in this wait until we get to the boundary strobe, because then we can advance onto the delimiter between CRC and the ACK. I need to remove that for very, very obvious reasons. It's sending the validity of the ACK. Oh, sorry, validity of the CRC on every cycle until that boundary strobe comes through. There we go. I mean, there's a lot of data there, which I don't think is correct. Look at the scope. That's not correct either, is it? Look, we've got multiple frames coming in. Oh, is this because we're hacking in a stupid place now? Let's go to idle here. Yeah, I think another state to wait in there would be required, because I think we're stomping on something and then the other node is trying to transmit again, kind of thing. Right, that's better. Although look at the red line. Oh no, the red line thinks it's coming into a new frame immediately, doesn't it? Okay. But yeah, because the ACK triggers a new frame. Okay. So yes, what we need to do is wait for 2 boundary strobes. I think that's a very good idea. So we can put something into counter. I think 1 will do it. MD sync. Like that. Oops. Trying to drive counter combination. Whoops. Okay. What do you reckon? Here we go. Yes, that looks good. And if you look at the scope, we're wrapped nicely up against the end of that ACK as well. In fact, I think we're sort of a half bit after the ACK. Let's just zoom in on that quickly. Come on. That is 1 bit. Fits into 3-ish segments. So we're at where are we? What? Put 1 bit into 1 vertical window. Yeah, so it's it's 1 sample point after the ACK. Is that correct? Okay, so we have the CRC happens, and then we wait 2 boundaries for the ACK. Then the ACK happens, which we are participating in now. Let's get rid of that just temporarily. Then we head on at the boundary strobe to the ACK delimiter, and then on the RX strobe we call it done. Yes, this is perfect. Blue is, I believe, the sample point, although it doesn't look like it. Oh, it's drifting really quite fast, actually, look. After 3 bits, I think we've drifted so far that we're almost at the bit boundary. Don't like it. I think we need to do something better about this clock. Hey everybody, I don't know what happened there, sorry. Hopefully you're still around. That's very frustrating. I think OBS crashed in a very subtle way, but I'm not entirely sure. So yeah, welcome back, hopefully. Right, where were we? We were talking about the ACK and the delimiter, and I think we're in the right place, and then it goes back to idle, and let's try without the ACK. I don't remember where we were now. That's annoying. Yay, welcome. Sorry, I'm not sure if you heard, but I don't know what happened there. I think OBS crashed in a very slow and subtle way, so I didn't realise for a minute. Okay, so here's our frame. That's working. Let's put the decode or the frame decode back in. I ceased. Not again. I'm running now, aren't I? Ooh. DLC valid, no. Why no? 3363. That looks good. It's working now, that's good. Oh, the CLC valid no. That's because we're giving 42, we're not giving 1. Okay. Right, so yes, the issue was that we were waiting for a strobe, and during that wait we were sending the state of the CRC over and over and over again. Now we're back in a good position though, which is cool. We can look at actually acknowledging on the bus. I just stopped streaming. Oh, sorry about that. Yeah, I'm not sure. I thought my internet went out because a lot of things failed. And then I was waiting for OBS to restart and it just locked up. So, yeah, never mind. Right, let's put our ACK in there. And I think let's be daring and remove the other node from the bus so that we have to acknowledge it. Should we try that? I think that would be kind of cool. So there it is. And we are both acknowledging at the moment. If I remove them from the bus. Here we go. Yes! That's awesome. We have now successfully received, CRC'd, and acknowledged a frame. Which makes me very happy. Woohoo! Party time! Maybe it's more biscuits. Date plus %s. Look at that. Awesome. Oh no, oh no, oh no. What's broken? Why have you broken? We were doing so well. But Glasgow safe. Glasgow on the bus again. Oh, no. Interesting. Keystorm, yeah, we can dance. The trouble is, we just found a problem immediately. Right, I'm going to reset my little CAN board here. That's going to put the bus idle again. I need to set it up again now. So, excuse me a sec. Okay. Oop, there's one frame. There's one frame. So we are doing the acknowledge, and they are not involved. That, you know, the other node on the bus is now completely disappeared, which is awesome. But what caused that little freak out just now? Let us put some special data in here. So frame length of 0, that works. 0, 0, that works. FF, that works. 5, 5, yeah. So if we do, so that's an 8-byte all ones payload, that works. 8 bytes, all ones. Okay. 8 bytes, all zeros. That works too. So what got it unhappy? Do you reckon it... That's a frame every millisecond. Oh, sorry, every 100 milliseconds ish. Not going to be accurate because we're doing it from Linux, but oh, there we go. Broke again. Yeah. And what is actually going on in this state? Put you on the scope so I can have an investigate and you can see what's going on. So if I do a single capture, we've got some errors after the frame. Okay. It looks like, yep, the individual frames. Oh, there's a pause there, look. I wasn't expecting to see that. Oh, there's, look, big gaps. Okay. And then for each of those blocks of attempted transmissions, we've got what? So the red indicates, what are we actually triggering on? We're triggering on the CAN starter frame. Let's trigger on, yeah, starter frame's okay. I don't know quite why it's, the red line indicates our framing in the FPGA on the Glasgow. And you can see sometimes it doesn't get the end correctly. Here, if we scroll over to the end of the frame, the key site, or the Agilent decode says question mark, question mark. And that is after 1, 2, 3, 4, 5 bits. Do you think that might be part of the problem, that we are so out of whack? Yeah, I think it is, look. Okay, let's make test data now. We've got a hypothesis. Got to reset it again. That's okay though, it's quicker the next time around. Let's turn the scope on again. Ooh. Right. So I think if we... Well no, because that should have happened with the zeros and the ones, shouldn't it? Send the date. Oh. That was very truncated. That's very truncated. And incorrect. Frame ID 1543. No. You're completely out of sync now. I think we filled up the FIFO or something like that. There was quite a lot of data coming through. There we go. Okay, we're in sync now. So this is where COBS would be useful because we'd never get out of sync like that, which I don't think is something we need to investigate right now. Oh, yuck. Immediately. Error. Reset. So you can see here, look, we've got, this is the frame, and it's just coming in over and over again. And I think this is because our, what's wrong with the oscilloscope? Yeah, I don't know, the decode's a bit wonky. So here is the frame, and it's happening over and over again. Same CRC over and over and over. There's a couple of massive blocks, and I think that is, so we've got 16, 15, 43, 6. Oh, it's not in there. Unexpected. 1, 2, 3, no. Oh, okay. I thought this might be a good example of the FIFO filling up. I think you're right, Omni. Yeah, so I was going to come to that, sorry. I think the issue we have is that when we have a large number of bits with no change, we have no edge to resynchronize on. And over that period, do you remember we were seeing that over 3 bits, our sample point was nearly at the bit boundary? I think that is the issue. So 3 bits is bad enough that our sample point shifts all the way to the end of the bit. If 4 or 5 bits, I think our sample point is going to shift past and into the next bit, which means that our bit boundary points are also going to be shifting by a similar amount. So our ACK is actually no longer going to be in the ACK position. It's going to be in the, grab the diagram. Our ACK is no longer going to be here. It's going to be shifted into the delimiter or the end of frame potentially. So yeah, we need to do something about this really. It's not in a good state at the moment. That again, so we can now send a frame. Although that's immediately failing because nobody's hacking it, or because it's bad data again. Let's get a frame that we can... sorry, one sec. Let's get a frame that we know is bad, and we can scroll up through here to grab one that we saw previously, which had that CRC. I can't remember what it was now. Do this a few times until we get a bad one, and we can catch it. Okay, not going to happen now. Yeah, Omni, exactly. That's exactly right. There we go. That's yuck. So 1, 2, 3. Frame ID of 1, 2, 3. Frame ID equals 1, 2, 3. There we go. 59E0. So this is a yuck frame, which makes it bad. And I'm going to store that. And I'm going to try playing it back now and see if it immediately blows it up again. I'm going to reset my CAN doodad. Let Glasgow up. Set up the interface again. So there's our test frame that I sent during setup. Okay, so 1, 2, 3, 16, 15, 43, 08, 04. Oops. I should have used dots here as well, that's annoying. Oop, yeah, bad immediately. One more time. Bad immediately. Cool, so we've got a frame that we know blows it up. I think I'm going to put the other board on the bus again so it can acknowledge things and we don't have to keep resetting everything. Okay, so Glasgow will acknowledge this, but it will probably make it unhappy. Network's down, right, oops. Okay. Ooh. Ah, look at the scope though. So we stomped on it, and then we stomped on it, and then they tried to transmit it again. Oh. And then it came through successfully the second time, but look, we were way out of whack. That's interesting. Okay, right, let's fix this clock, because that's clearly the major problem right now. And that needs to happen. I think the 48 megahertz clock is enough, but it's here in the CAN timing that we need to fix it. So we can play to our current baud rate. We know it comes out as 19.2. That 0.2 means that every 5 bits, we need to have a 20 cycle doodad. Yeah. So that's +1. Right, to make that happen, where do we go? I think we need to round the value. We need the value so that we can tell the difference. So let's grab that. Oops. Can you sample the counter on the edge and shove that in the FIFO? Sample the counter. Yes. Oh, just to see what it is. And then do what, like divided by 19.2 or something. Or do a worst case data like a 5.5 or AA. So are you, Omni, are you trying to compare the FPGA's 48 megahertz crystal and our 19.2 proposition versus the transmitter's clock? Yeah. I'm pretty confident that the error is the 0.2 and that 0.2 folds up into 1 over 5 cycles or 5 bit times. So if we did 19, 19, 19, 20, 19, 19, 19, 20, I think we'd be in a good place. And because we're in Python, we can actually do some reasonable calculations about. You want to see that actual number? Okay. Let's see then. You want. Well, Keystone is Python, but the gateware is in NMyGen. So at build time, because I know that the target bitrate is 250k bits, I can do a whole bunch of Python stuff, magic, to produce two values, like the 19 and the 20, for example, and then I can produce like a little array, and then once I've got that array in the gateware itself, I can then sort of squish it down and make use of it more properly. Does that make sense? Yeah, so you can kind of augment the gateware with really quite flexible, complex Python. What are we trying to do? So we're trying to get the counter out. The counter is here, 32 bits is massive, but whatever. Let's suspend edge cut. You want to know the counter here. You want an if edge sample count and put that in the FIFO. Oh, okay. So what? Reset this sample. So we can actually do this at a much higher level, can't we? We don't need to deal with the timing module as such. Don't do a reset. No? So every edge, you want the new value of the counter as it's incrementing over and over again, incrementing. Okay. Yeah, in FIFO. Let's do it in the CAN timing module because we've already got the edges there. And then when we have the edge, need to keep the FIFO. Sorry, Keystorm. So you get to learn both digital design and Python. Yeah. Just look at what the counter is when the edge comes, since this should correspond to what the error we have at that point by comparing it to the ideal count for a bit. Yes, okay. Don't forget that the difference between two counter values isn't necessarily 1 bit time. I feel like this is going to get quite complex to get the data into the FIFO. I can just turn all of this off, right? This is yucky code, but we'll just go for it. Oh, actually, we can do shifting and stuff, can't we? T equals T 8 to the end. There we go. X is greater than 0. Oops. So that should now, on the edge, it should trigger 4 bytes into the FIFO, which we can then read out as a counter. Yeah. I'm going to comment out all of that again. No. The counter just goes up and up and up. In fact, it's not doing anything at the moment, so let's make it happen. So this is all that's happening at the moment. And I don't think it's going to build. I thought that's what you wanted, Omni. What? Boop. Sorry if I misunderstood. You said not to reset anything, and I thought you meant don't reset the counter. There we go. Oh, it's memory. There. Don't do any new resetting. Oh, okay. Well, there we go. So that is now a backwards counter. Yes, that is backwards. Why is that backwards? Right, okay. So now we have the values between each edge. And yes, indeed, I think, yeah. Import struct, I think. I can't remember the doodads for this. Dot unpack format buffer. Unpack, and then I think it's a no idea on the endianness. We can poke it until it works. I hate endianness. I can never get it straight in my head. Unsigned int, capital I, that's what I was going for. I counter. There we go. Okay, I'll put the reset at the bit period back in. Boop. Didn't like that. Bytes like object is required, not a list. Oh, right, fine. You can have the raw results of the read. And then we can put the endianness in. Okay, that's... Oh, that is probably correct. It's all incremental, isn't it? Boom. Don't like tuple int. Oh, right, okay. Boom, there we go. So we're getting about 188. Looks like the bit time. Let's do a min diff. There's lots. I'll get back to it, sorry. Is min diff. There we go. Okay, so a bit time is coming out here as 187 counts. Yes, that's a very good idea. Let's put 555. 55555. Oops. Boop. 187. 183. This should give us the ability to decode the message. 188, 196, 188, 196. So that looks like an alternating 1010, doesn't it? A little bit asymmetric, but never mind. 100, yeah, 180, 188, 190-ish. Why were we getting 19.2? Ah, because we're doing the time quanta, we're not doing the entire bit. So 188, oops, 188 divided by 10 is 18.8. And we were getting 19.2. Don't forget that we see here, so we've got 188 versus 196, because it's a little bit asymmetric. So 196 plus 188 divided by 2. 190. Oh, look at that! It's 19.2! Oh, that makes me quite happy. No worries, Omni. Divide by 2. No, not divide by 2. Divide by 8. 10. There you go. Yeah, so that is spot on with what we were expecting. I'm also going to add in here the polarity of the signal as it stands, which is what it is, self dot rx trigger, the inverse of. Yep, sure, see you in a sec. We want a unsigned char B. Node 2. Blah blah blah. B, okay. B. So that says it's level and the counter. Requires a buffer of 8 bytes. What? Let's do a C. No. Surely I don't need to have a square or multiple of 4 bytes here. Bytes of length 1, standard size 1. Let's do a C there. I don't think that will help it though. Oh. Oh. It did help it. That was unexpected. Yeah, that's not right. mind. That would have been nice. I suppose I could put it. I could still put it after. Let's do that. Never mind. Okay, I think I might be going to pack up soon. Come on, what? Oh, I did 5. Okay, 4. There we go. Unsupported upper hand. Level's not defined, of course. Yeah, so I think that satisfies Omni's curiosity. And it also shows that everything looks like it's in line, which is good. It is what we expected. So now we've got to figure out a way to to modulate effectively the width of a time quanta. Oh, a time quanta. Okay, so we've got 10 time quanta per bit. And that does potentially mean that we have the ability to deal with that point x over the duration of a single bit. So at the moment it's coming out as 19.2, but if it came out as 19.3 or 8 or whatever, then we can still deal with that by putting the last time quanta to be n plus 1, for example. Okay. I'm going to keep that test for Omni. Check out a new branch, Omni. There you go. Struct. Yes, yes. Hopefully we can get rid of most of this. We're keeping these bits. Yes, on that. Okay. Oops. I want that. Cool. We can come back to that if we need to. What branch were we on? We're on CAN sniff. Okay, so this should be back now at the position we were before. Now we've got, yeah, because we're doing 10 quanta per bit, we can now put that last significant bit, or the first decimal point, into the last time quanta, and that can go in here. Yeah, because they add up to, okay, yep. So actually segment 2 is now going to be 3 plus that first bit. So bit psych is equal to, grab that, is 19.2 for 250k bits per second. Am I getting this right? No, we don't want a whole extra one in here, do we? We want this to be times bit psych. No, we don't even want that. Oh no. Yes. Okay. So we want that to be plus fix. Let's call it such that we get the extra 1 tick. Do we round it? No, we floor it. There, so that becomes 19.0, just 19 dead. And then the bit psych fix is going to be the difference between the two times 10. And it's then going to be that rounded to an integer. And this will mean that if we print out these, bit setup psych should be, well, let's calculate that in a second. So we reckon that the total period is 192 ticks. This is going to be, oops, 19 times the 133, so that's 7. Oh, that's 19 times 7, sorry, so that's 133. And then this one is going to be the 19 times 1333, so that's 10, 190, plus the 0.2, which is multiplied by 10, which becomes 292. Yeah, that works. Shall we see if it actually works? Oh, it does. Okay. Let us retransmit that nasty frame we came across, which was 16, 15, blah, blah, blah. There we go. Ooh. Okay, so looking at the scope, we've still got that frame coming out twice. Oh, and it says frame length 11. Oh, it's got out of sync now, hasn't it? There you go, okay. Let's restart Glasgow. First time it comes through. 1, 2, 3, 5, 60. Yeah, okay. And then we get upset. If I put Glasgow into safe mode, we can see the ACK clearly. There's the ACK. Okay. And now if we put Glasgow into run mode, right. I think those are the sample points we can see there, and they are in the wrong places, look. So that's a different frame. and it's not got this problem. So it's the 04 as the end, which seems to cause issues. It's either something to do with the CRC or it's something to do with the payload, and it just causes us to drift a little bit too far. I think it might be the CRC, the FE potentially. Okay, I think this is a job for next time. Hey Omni, welcome back. You'll be very, very pleased to know. I stored it on a branch for you even. I was that pleased that the little test we did came back exactly as we would have hoped. So let me just take a note of the to-do items. So the shift register, I think we can cancel that. So that's effectively done. Oops. Termination to do, verify the termination works. Why am I putting lots of T's in there? Variable, baud rate via the command line arguments, handle bit stuff errors and frame errors. Okay, what we want to do is fix up the clock rate, the clock on bit rate, because it's not good at the moment. So I think I'm actually going to pack up now, Omni, but I am going to just grab this for the commit. Yeah, okay, let's keep all of this. But first to try at handling the clock error as back. Okay, so if I check out your branch and I run the application and I do a 5555, so worst case, like number of edges, we get this, which is great. Here you can see the 196, 198, 188, 196, 198, and that's the slightly asynchronous or asymmetric shape of the waveform. And if we have a look, 196 plus 188 divided by 2 is, and then divide by 10, 19.2. So we're bang on, which is good. We just need to handle that. And what I realized is actually we can handle the whole digits the way we have previously been doing it, and then we can handle the first decimal by dealing with it in the so you just count 192 of those ticks. Yeah, well, what we can do, if you look here, is we can put an extra tick in the last time quanta. Does that make sense? So here we can go for 19, 19, 19, 19, 19, and then here we can go for 22 or 20 or whatever it needs to be. And it shifts the sample point in the frame, but only just. So I think that's probably plan of attack for next time. But yeah, I'm gonna tidy up now, I think. Good stream of doing, yes. I hope it was enjoyable. Thank you everybody for watching, and lots of new subscribers today, so thank you everybody for subscribing. I will hopefully be around again next Wednesday, and we can continue on this. I've been tempted to do more on the Hub 75 panel, so I'm not sure if we're maybe going to do a bit of that next week, I don't know yet, but yeah. Separate bit time counter and time counter. Yeah, that's an interesting idea actually. Let's think about that next week. But yeah, thank you everybody for watching. I'm going to run off now, and I shall speak to you all soon. Bye.